Okay. So in the last session, we stopped here. We understood calculating the mean vector for two-dimensional points, right? So we take the average of all the x points, uh, and we take the average of all the y points, and we calculated the mean vector. This is where we were right in the last week, right?
Yes,
Okay. So today we are going to understand covariance. So we know what a variance is, right? Variance just measures how spread the variables are from the mean. The dispersion of the data points from the mean is what variance gives us, right? So if we take one-dimensional points, something of this sort. If you take one-dimensional points, and if the points, let's suppose the mean is somewhere here. Let's suppose the mean is here, and what variance actually calculates is how far uh, the point stretched from the mean is what actually variance measures. Variance actually gives us this distance, right? How far the point spread from the mean is what variance gives us. But when comes to two-dimensional space, we have two dimensions, right? The one is x-axis and the other one is y-axis. Okay. So now when I represent the points on this coordinate system x and y, they look something like this. Let's suppose these are the points I do have. Now, if I stretch these points onto x-axis, I'll just bring back the x part of these points onto this x-axis. Okay, now similarly what I'll also do is I'll bring the points onto y-axis. I'll just represent the y part of that particular point onto y-axis. Okay, so I'm just bringing these points or placing the y coordinates of these points onto y-axis. What does that actually means is, let's just take a simple example. Let's suppose the point is 2 comma 3. So what does that point means? On x-axis the distance is 2, right? On y-axis the distance is 3. Then that is the point which is 2 comma 3, right? Similarly, now if I bring that point onto x-axis, it falls at 2. When I stretch that or mark that point on y-axis, it stays at this point, right? That is how the points looks like. Now if I take the mean of those points, how does they appear? Let's take it this way. Like, if suppose this is the mean on x-axis, let's call this as mean, and the point stretched from here to here. So this is the variance of x. How do we represent variance? Represented by this way, right? Sigma x square is the variance along x-axis. And if you want standard deviation, it is just the square root of variance, which is sigma x square. And if I consider this as mean on y-axis, this would be the variance on y-axis. How far the points dispersed from the mean is what variance measures, right? So that becomes sigma of y-axis, y square, which is the variance along y-axis. But now we know the variance along x-axis and variance along y-axis, how the points are dispersed along x-axis and how the points are dispersed along y-axis. But now in two-dimensional space, we also have to understand how the dimension x is influencing the y-axis. Okay, how the variances, I mean, it basically measures how the y coordinate or y dimension points or y dimension is changing with respect to the x dimension, is what actually covariance measures. Now we are actually trying to understand the variance between two coordinates, or how the points are changing. If one dimension is changing, how the points on the other dimension is changing is what covariance measures. So you all remember what variance is, right?
yes,
Can someone tell me how to calculate variance of points in one dimensional space? or it's two-dimensional space, how do we calculate the variance?
1 by n summation of xy minus mean whole square
Xi minus
minus mu whole square.
whole square.
Yes,
So from I is equal to 1 to n, right? This is how we
yes.
calculate the variance. So what variance actually tells us how far or what is the dispersion of the data points from the mean is what actually variance measures us. And now how do we calculate the standard deviation?
Applying square root to it.
Square root to this. What is the difference between variance and standard deviation? Let's others answer this, Ashwin. What is the difference between standard deviation and variance? Can someone answer this? What is the difference between variance and standard deviation?
Standard deviation is the square root value of variance.
Yeah, that's right. And why do we calculate standard deviation? Why not covariance? Why covariance is, I mean, variance is not sufficient to calculate the dispersion of the points from the mean?
It's a long distance, so we calculate the standard deviation.
Long distance in the sense.
To nearest to the mean, it becomes long, so we calculate a standard deviation.
No. Why it's becoming long? I told you about units of variance and units of standard deviation, right? In terms of units, what variance is doing and what standard deviation is doing. We were talking about that, correct? Yashwant?
Yeah, variance would be in squared units, whereas standard deviation would be same as the point units.
Yeah, that's right. So variance, when we don't square it, what we are doing, we are squaring the units, right? So we are just squaring the units. So the units will become squared. So the data points unit will be squared here. But when we apply square root to this, it will be standardized to the units of the data points. So that is what the difference between standard deviation and variance. Now standard deviance or variance will give us the dispersion only in one dimension, right? Whether it is on x-axis or y-axis, but it will not give us the dependency of one dimension on the other dimension. So that will be given by covariance. So if you look at the description of covariance, it is a statistical measure that shows the extent to which two random variables change together. So two random variables. What is a random variable?
When an event or experiment is happened, then based on the outcome which we select a variable is called random variable.
Right. So the outcome of any experiment will be assigned to a random variable. So let's suppose if you are taking two random variables, I mean you are conducting two experiments and if you're getting two different random variables, this covariance actually studies how one random variable is impacting the other random variable. Okay, that's what basically covariance actually calculates. The extent to which two random variables change together If you take the example, let's suppose one random variable is smoking, and the other random variable is health. Let's suppose. So how the if a person is smoking more, his health will be his health condition would be like critical. If he is smoking less, his health would be little better when compared to this. If he is not at all smoking, his health would be so great, right? So now we are studying the impact of smoking, which is one random variable, on the health of a particular person. So let's suppose smoking is in what kind of random variable it is. It is what we call um, numerical random variable or categorical random variable or attribute, you can say. Smoking is what is like no smoking, no smoking. Let's suppose this is no smoking and this is smoking. Health is low, I mean health is high, medium, low. So what I'm saying is covariance actually gives us how the random variable smoking is impacting the other random variable health. How they both are correlated. How one parameter is impacting the other parameter is what actually covariance measures, right? So now the question is, what kind of random variable is this? Smoking. Categorical or numerical?
Numerical.
Numerical.
Categorical.
If it is categorical, whether it is nominal or ordinal.
It would be nominal.
Okay. What
Nominal.
is health? It is categorical or numerical?
Categorical.
Nominal or ordinal?
Nominal.
Ordinal.
Yeah, it's ordinal because we have an order, low, medium, high. We have some order here. Smoking, it's just like there is no specific order with it. You can draw it in the other way as well. Order or no, smoking or no smoking. They can be just binary variables as well, 0, comma 1. So now we understood, right? So you are trying to understand, let's suppose if I have some data points like this, if some points, if you stretch all these points onto x-axis, what you will be able to study, how the smoking status, how dispersed the people are with their smoking status. Let's suppose on an average, if this is the mean, let's suppose this is the mean of all the smoking people. On an average, one is the mean of all these points is 2, let's say, like 2 hours. So on an average, we have 2 hours smoking time for each person of these data points. Now you can understand the dispersion, how spreadly, I mean, how the points spread around the mean is what variance along the smoking dimension is gives us. And if you stretch these points onto health coordinate system or health axis, it gives us what is the mean of the health of these data points and how the variance. I mean, it tells us how many people are more healthy or stretched or dispersed from the mean, and how many people are stretched lower to the mean is what basically variance along the health coordinate system actually gives us, right? What that actually gives us, what information you can gather from that is, uh, so let's suppose if you're considering only variance along the x-axis, so if you know the mean and if you know the dispersion, you can actually try to understand the data, like if the people are more addicted towards or the people are less addicted. That's what you can say, right? So if you just take only the variance along the smoking, what it actually tells us, if the mean is high, you can understand that these people are more addicted to smoking. If the mean is less, what it says, the people are less addicted to the less addicted to the smoking. If the variance is large, what it says, so it is random phenomena. Like there are people who is smoking more. There are also people who is smoking very less. If the variance is more, we can say there are different kinds of people. They're not completely addicted to it. But if the variance is less, what it says, they all comes to the same zone. It means like there is an influence on each other is what we can say, right? So if everyone is around in with low variance around the mean, what we can say is there is an influence between the smokers. That's the reason they might have all started at the same time, and they might have all influenced by each other. I mean, if let's suppose if you take this example, if all the friends are going for smoking, they all smoke for the same time, right? So they have influence on one another. That's why if the variance is large, they may go alone and smoke. If the person is going, I mean, individually, we can say they are not going in group. There is no influence on one another, because one person is smoking for very high time. It means like he's completely addicted. He takes his own time. But if the smokers are around the mean, it means like they're going at the same time, but little variance. One might miss in one iteration, other might miss in one other iteration, but they're all almost like in the same zone. That is what variance along the smoking says. But variance along the health is also say does also says the same. But the influence of smoking on the health is determined by this covariance. Is that clear? Hello.
Yes.
Yes.
Yeah, so that is what covariance is, just like the dependency calculator, a statistical measure that shows how one random variable is changing with respect to the other random variable. Now let me write few diagrams, and let me extend you like how does this actually looks like. How does a posit there are different types of covariances. If you look at this, one type of the covariance is positive covariance, other one is negative covariance, and the other one is zero covariance. Let me represent these in geometrical representation, so that you will understand how does positive covariance looks like, how does negative covariance look like, and how does zero covariance looks like. So what does positive covariance says is that if the covariance between two variables is positive, okay, that is what positive covariance means. It means that when one variable increases, the other tends to increase as well. How can I represent that? So if one variable is increasing, the other variable will also increase, is what it is saying. Let's suppose I have two dimensions. If x is increasing, y is also increasing. Okay. So you can predict that, right? So if you look at these diagrams, when x is increasing, y is also increasing, right? Look at the trend. So this is if the data points are correlated like this or dependent like this. So when x value increases, y value is also increasing. As we move forward, y value is increasing. As we move forward, y value is increasing. So this is called positive covariance. When the value of one random variable is increasing, the value of the other random variable will also increase, tends to increase. Okay, so those kind of data points those kinds of data points are told to have positive covariance. Now, what is negative covariance? Negative covariance is just the opposite to positive covariance. It means that when one variable is increasing, the other variable is decreasing. Okay. So if you want to represent that in 2D, this is how the points looks like. When x increases, y is decreasing, right? So the x value is decreasing when y value is increasing. Okay, look at this. When low x value is there, we have high y value. When we have high x, we have low y value. So the trend is decreasing. Okay, so then we can say it has negative impact. The variable x has negative impact on y. Understood? So that is what negative covariance is. You can take any examples. So you can say this is smoking, as we told, and their health, or work activity This is work activity and this is their health. As we do more workout, we will be more healthy, right? Uh, the smoking and health will not be fall under this category. Sorry, when we smoke more, health would deteriorate. So that comes under negative covariance. When we smoke more, the health will automatically decrease. When we smoke less, health will be more, right? That is an example of negative covariance. So the impact on smoking on the health is negative. The impact of workout on health is positive. Okay, that is what uh, you know covariance actually means in terms of intuition. Is that clear?
Yes.
Okay, now let's understand what is zero covariance. The zero covariance says if the covariance is also close to zero, it indicates that the two variables are not linearly correlated. Okay, so the two variables are not linearly correlated. That is what actually zero covariance means. So what is not linearly related means? So there is no relation between the two random variables that we are choosing. Can someone say me the example of that? No covariance. There should not be any relation between the two random variables is what zero covariance means. This is how the diagram actually looks like. So if you look at this diagram, if the data points are like this, there is no relation, right? Whether it is positive or negative trend, there is no relation between any of these data points. If we go to the if you are going towards an increased x-axis, you have high value, you also do have negative value. If you increase the x also, you have high value, you have low value. So there is no direct relation between these two variables x and y, like how we see here. We have a positive relation between the x and y. The example is work activity and the health. When we do more when we do more workout, our health will be so good. That comes under positive covariance. When we smoke more, our health will deteriorate, right? That means like there is a negative trend between these. There is a negative trend that is called as negative covariance. The zero covariance means there is no relation between these two variables x and y, so they are independent. So such kind of relationship is such kind of data points distribution is said to have zero covariance. Okay, can you tell me the example similar to what I have told here? Workout health, smoke health. Can you tell me two events which are independent of each other?
So smoking as well as healthy, being healthy.
Smoking and being healthy is an negative trend, right? Like when we smoke more, our health condition would be much worse, right?
So
When we
I'm
smoke
saying
less,
that like the person is healthy, but he will smoke. That is, there is no trend between those two, right? So it will fall under zero covariance.
no, I mean, if you consider most of the data points in general, the smoking is a bad habit. So when there could be some points which we have already heard, you know, like what we say outliers. So one can smoke high, but his health would also be good. But we are talking about the general trends. So such kind of example, like if you take about, uh, you know, um, age and the marriage, there could be positively correlated when the age is more, negatively correlated. Age is more, marriage condition would be always true. Uh, what when we say
Cooking, driving.
what?
Cooking, driving. Cooking,
Yeah.
driving.
Yeah, right. So that would be also an example. If the person who is cooking will have his driving skills, there is no correlation between his cooking skills and the driving skills, right? These two are independent activities. So one who is cooking good can drive very good. One who has less cooking skills, they can drive. They doesn't necessarily needs to be drive good or worse. So there is no correlation. I mean, there is no relation between these two random variables. So such kind of examples comes under zero covariance. These are the data. When I say data points, data point is nothing but the representation of a person, right? There could be one person whose cooking skills is low, but his driving skills is more. There could be another person. Each data point is the representation of one person. It actually represents when the cooking skills is high, this is where it falls. When the driving skills is low, it falls here. So that is what each data point means. And this is the distribution of the sample that we have taken. And we are trying to study the relation between cooking and driving skills. And we understood that there is no relation between these two random variables. The reason being the covariance, when we calculate the covariance, it is zero. So now in future, when someone asks you to calculate the or to when someone asks you to understand the relation between two random variables, what you have to calculate? You have to calculate the covariance. Once the covariance is calculated, based on the result that you have got, whether it is positive, whether it is negative, or whether it is zero, you can predict that this random variable, I mean, when we calculate the random covariance of these 2 points, I have got positive result, which says they two are positively correlated. And when I get negative result, it means that they are negatively correlated. When I get zero covariance, it means that there is no relation between these two random variables. Okay, so the impact of one random variable, or the impact of one action is resulting the other action, and how that is resulting, whether it is resulting or not, highly, I mean, it is impacting it in the positive direction or negative direction, is what covariance basically studies. Now if you quantify this, let's suppose I have this example again. How do you quantify the relation between these two random variables? I'm now drawing two diagrams. Okay, let's understand how that is looking for you. So this is one diagram that I have given to you, and this is the other diagram that I have given to you. Okay, so now tell me, these two diagrams, this is my diagram 1 and this is my diagram 2. Okay, now tell me whether they're positively correlated or negatively correlated, or zero. I mean what, whether they're positive. This diagram is positive variance or negative variance or zero covariance. By just looking at the points, what you could predict.
Positive, positive variance.
Positive.
Both are positive covariance, right? For both the diagrams, the covariance is positive. Now, tell me, let's suppose this is x, y, and x. Okay, this is x and y. Now, tell me how the relation between x and y is that strong. The dependency of y on x is very strong or very less. Where it is strong out of these two diagrams, 1 and 2, and where it is less.
For first diagram, it is strong.
It is strong.
Yeah, because both are in same trend, right? X is following Y.
X is following y. So when you calculate the covariance for this, let's suppose you're getting that as 42. When you calculate the covariance for this, you're getting it as 21. Okay. With these values, like if you get these values, the covariance is high, then you can say they are like the dependency between these two random variables is high. As this value is little less, you can say the variance between these 2 points is little less. Okay, but there is no specific boundaries for the covariance can go to 100, 200, 300, 400. It can also go to infinite. Okay, so you cannot strongly predict, you cannot say 42 is a strong relation. When you compare two diagrams, you can say that this distribution is has high dependency between the random variables when compared to the other distribution. When you're comparing two distributions, you can say that. But by just looking at the variance 42, you cannot predict whether that is high or low or medium, because covariance value can extend still infinite value. Okay, so now there is no specific boundaries to say these are highly correlated or not. Let's suppose I have something like this, like -1, 1, 0. Okay, when I'm getting the value, if I say covariance is 1, then they are highly correlated. If minus 1, if it is like highly, like less dependency, or change is very less when the covariance is 1. There is no specific boundary of that sort. If there is a set boundary for these values, then you can say when you are reaching to 1, they are highly correlated. If you are reaching to minus 1, they are negatively correlated. You can say that, but the covariance values can always extend from minus infinity to infinity. So you cannot say how strongly those two variables are dependent. So that is the drawback of covariance. You can say the direction of the dependency, whether they are positively dependent on each other or negatively dependent on each other, or they are not at all dependent on each other. But you cannot say the strength of the dependency, because when you get some value, it is you don't have any boundary to compare, right? Let's suppose if I say, if 100 says, if covariance of 100 says the two variables are very strongly related, if I have such boundary, I can compare with this boundary, right? I have this 100, so I can say 42 is 50% dependency is there between two variables, is what I can say. When I don't have this boundary, when I say the boundary is infinite, you cannot say how strongly those two are related, but you can say they are positively correlated. The trend is positive. I'm just confusing you, but that is what covariance is, not correlation. Covariance is what says the dependency between two random variables. So what it just say, it says whether it is positive trend or negative trend or no trend, but it cannot say the strength of the dependency between these two variables. That is what I mean to convey here. Understood? So I'm just repeating, variance is measured in a particular dimension, whether it is on x-axis or y-axis. Covariance actually measures, the dependency of one random variable on the other random variable. That is what covariance actually will do. It shows the extent two random variables change together. There are three different types of covariance. We say positive covariance when the value is increasing with the other random variable, when the value of one random variable is increasing with the other random variable. Okay, if the covariance between two variables is positive, it means that when one variable increases, the other tends to increase as well. The negative covariance means, it means that when one random variable increases, others tends to decrease. We have seen the diagrams. And zero covariance means no relation. We also have seen the examples. The health status with the smoking is negatively correlated. Workout activity versus health is positively correlated. Cooking skills and driving skills have zero covariance. Sorry, positive covariance, negative covariance, and zero covariance. And now the final conclusion is covariance can just say the direction of the dependency, but it cannot specify the strength of the dependency, because it doesn't have any boundaries set. The boundaries of the covariance is minus infinity to infinity. So when you get any value, you cannot compare that with infinite value. So you cannot specify how strongly those two variables are dependent or not, how strongly these two are dependent. To overcome this, we have another concept called as correlation. Okay, covariance and correlation, they both says the dependency of one variable on the other variable, like covariance and like variance and standard deviation. Covariance and correlation also says the same, but correlation basically also tells you about the strength of the dependency. Along with the direction of dependency, it also tells you the strength of dependency. Okay, how does that tells us the strength of dependency is what we are going to learn now. But I want to make sure you're clear with what is covariance and different types of covariance and with examples. Is this clear? Hello?
Yeah.
Yeah, it's clear.
Yes, Mohan. Yeah, yeah.
Okay,
It's
okay.
clear.
Yeah.
Okay.
Okay, okay.
Yeah, it's just simple like this. So you have to understand the dependency of one variable on the other variable. So you just have to remember these examples, like health status with workout activity. As you do more workout, your health will be very good. When you do low workouts, your health will be low. So if you consider those two examples, those two activities, so what is the relation between those two? That will be positive always. So if one increases, other will also increase. If you take the other example, smoking, when you smoke more, your health will be low. When you smoke less, the health will be more. Health status will be more. So if one is increasing, the other one is decreasing. If one is decreasing, the other one is increasing. That trend comes under negative correlation. And as you said, like cooking skills and driving skills, there is no relation between those two data points. So such kind of things are said to have zero covariance. Okay, so it actually tells us only the direction, not the strength of them, because you don't have any limited boundaries for covariance calculation. It always extends to infinity. So when you get some value like 42, you cannot compare that with the infinity to mention how strong the relationship is. Yeah, yeah. How do you say, like, if you compare this with infinity, is 100 is high, 120 is high, 1000 is high, 1 lakh is high? You cannot even say they are strongly related if the covariance is coming as 1 lakh, because the boundary for that is infinite. Covariance can also extend up to infinite, so you cannot compare the value. So you cannot use covariance to measure the strength of relation between two random variables or two dimensions or two attributes. It is just used to calculate the uh, dependency or trends in the data. That's all. Whether it is positive trend, negative trend, or no trend between the two random variables. So that is how actually covariance. That is the intuition of covariances. So how do you calculate the covariances? This is the formula of covariance. This is the formula of covariance. So what is the variance of formula? Variance is just calculated by using 1 by n, sigma I is equal to n xi minus mu whole square, right? As now we have two dimensions, we are just spreading this to two dimensions, xi minus x, yi minus y bar. So x bar and y bar is just the mean points. X is the mean of the variables x, y is the mean of y, xi and y are the individual data points of the variables x and y, n is the number of data points. This formula calculates how much the value of x and y deviate from their respective means and multiplies the deviation to understand the relationship. Basically, we calculate the covariance to understand the relation between x and y. Okay, what is the relation between x and y is what will be calculated when we calculate the covariance. Now, I have this example here. We want to calculate the covariance using this formula. How do we calculate the covariance for this example? How do we calculate the covariance for this? So what do we calculate first? We calculate the mean. Once we know the mean, we just apply these two data points, something like this, to this example. I mean, to this formula. So now let's break this into steps. What is the mean for these data points? Can someone calculate that quickly? Mean for these data
It
points.
would be 67.
67 is x-axis, right?
Yes.
And what is the y?
One 150.
153.
150. Yeah.
So now how do we calculated this mean, Madhu? How can we calculate this mean? Chintu, Valli, how can we calculate mean of a data point?
Sum of digits by total number.
Yeah. So sum of digits by total number of digits. So we calculated this by 65 plus 66 plus 67 plus 68 plus 69 by 5 will give me 67. Wait, 130 plus 145 plus 150 plus 165 plus 175 by 5 will give me 153. Now if I have to calculate the covariance of using this formula, can you three tell me how can I apply this formula to these data points? How can we now if I apply xi yi with the summation, what this becomes 1 by 5 when I is equal to 1, what will be xi?
65,
Yeah, 65 minus
67.
67,
67. And what is yi?
130,
130.
130 minus
153.
153. And what comes next? What should I apply here?
66 minus 67.
No, should I multiply or I should apply summation
Plus
plus?
Summation.
Okay. Now what is the next?
66 minus
66 minus 67. What is the other
So
point?
145.
145 minus 153.
153.
Okay. Now that's how you calculate the variance. That's how you apply the
Covariance.
formula. So now if you calculate the whole thing, what it becomes 1 by 5 into 6 minus 65 minus 67 is minus 2 into 1.
Minus 2.
130 minus 153 is minus 13.
Minus 13.
23, right? 13, 23.
Okay. 23. Minus 23.
Plus 66 minus 67 is minus 1 into
It's 1.
145 minus 153 is
Minus 8.
minus 8.
Not
Now,
done.
can you, from your side, can you calculate the other 3 points and tell me what is the final answer? And what that final answer specifies to you? It says positive, negative, or zero covariance.
One ten. 110 by 5.
110 by
5.
110 by 5. Okay, what is the value of this?
22.
22. So now you calculated the covariance of these data points, which is 22. Okay. Now you calculated the covariance of these data points. Now what this actually says, whether it is positive covariance or negative covariance or zero covariance.
It's a positive move.
Yeah, it's a positive covariance because you got a positive value, which is 22. So it says like when height is increasing, weight is also increase. Weight will also increase, is what you can say. When weight is increasing, height will also increase, is what you can say. Okay, that is what actually covariance means. How strongly height and weight are related, you cannot say with that with by calculating the covariance. Okay, you can just say if one is increasing, the other will increase. Okay, as height increases, the weight is also increased. Only is the only thing that you can predict with the covariance calculation. Are you clear with this, with covariance?
Yes.
Okay, you're clear, right? Everyone is clear, right?
Yeah.
Yes.
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 Okay. Now go back to correlation. I was talking about difference between correlation and covariance, right? Correlation actually tells us the strength and the direction. When I say strength, what is strength means? Strength means how strong health and weight are related to each other, how strong they are. So are they very strongly bind with each other? Or like they are not at all, they are negatively bind with each other, or they are not at all bind with each other is what it says. Why it is able to say the strength means, unlike covariance, which shows the direction of the relationship, correlation also standardizes the measurements to a given value between -1 and +1, making it easier to interpret. So unlike covariance, which takes any value between -infinity to +infinity, correlation just takes the values only between -1 and +1. Okay, so that is the difference between correlation and covariance. Covariance can take any value from -infinite to infinite. Correlation can take just values between -1 to +1. So if you're getting correlation as -1, you can say they both are strongly correlated, but with in the negative direction, in the decreasing direction. Okay, when you're getting correlation as 1, it says that they are strongly dependent on each other, or you can also say they are strongly correlated. If height and weight are strongly correlated means if one is increasing, the other will also sharply increase. Okay, that is what correlation means. How strongly two random variables or two attributes are dependent on each other is what it actually says us. Okay, that is the only difference between correlation and covariance. The correlation coefficient lies between -1 to +1. Correlation coefficient 1 indicates perfect positive correlation. It means as one variable increases, the other increases proportionally. R equal to -1 indicates perfect negative correlation. As one increases, the other decreases proportionally. It's similar, but it says the strength as well. How does it can specify the strength is what is written here. When R is equal to 0 indicates no linear correlation. There is no correlation between these two variables. There is no relation between them. There is no linear relationship between the variables is what correlation says. So it always tells you only the linear relationship, okay? Whether it is covariance or correlation, it is always tells you about the linear relationship only. Linear means the points, how the points are uh, spread along a particular line, or how they are spread along the linearly is what it actually means. It only tells you about the linear relationship between the variables. So look at, just read this point. The closer R is to 1 or -1, the stronger the relationship between the variables. Value close to 0 suggests a weak linear relationship. So let's take the example 1, -1. Whether if it is -1 or +1, it means like they're strongly correlated. They have strong relation between the two variables. If it is 0, there is no relationship at all. If it is 0.5, they are 50% strongly correlated. If it is -0.5, they are like 50% dependent on each other, like half of the maximum value. When you say -1 strong, when you can compare 0.5 with -1 and say like it is not that strongly correlated, but it is like 50 they are like 50% correlated with each other is what you can say. You can compare -0.5 with to -1. As we move towards -1, the dependency between the variables increases, and we move towards 0, the dependency between the variables decreases. So this is strong, this is no. So you're going from no to strong. As the value increases, the relation between them increases. When you say negative, it is in the negative direction. When you say positive, it is in the positive direction. So that is the only difference between correlation and correlation and covariance. Whereas correlation says about the strength and direction of the linear relationship between two random variables. Whereas covariance just can tell you only the direction of the linear relationship between two random variables. Understood?
Yeah.
Yes, ma'am. I have a question here. So why do we calculate covariance actually? Because as correlations gives us both strength and direction, right?
Yeah, that's how in real world we always, it is just for like a strategical understanding of the concepts. But in real world we always go with covariance. I mean correlation. We rarely use covariance when we just want to understand only the relationship, and we don't want to know the strength between the random variables. We just want to know whether it is just positive trend or negative trend. We can go with covariance. When you also want to understand the direction and strength, so if you want to also when you're studying the relationship between two random variables, when you also want to understand how strongly they are correlated, then you go with correlation. But you can always go with correlation. That it is up to you and what kind of study that you're doing.
Okay, got
So
it.
that's how you can choose. When you say standard deviation and covariance, it also applies the same. Okay. When you have positive covariance, what it says, when you have standard covariance, you can just interpret whether it is how much the spread is. But if you want to know the exact values, you always have to go do standard deviation. So you are just looking at the concepts, but when you apply this on the computer at large scale, the computing speed is very much needed to perform these calculations, whether it is matrix multiplication or performing square roots on larger data sets. It needs a lot of computing power. It needs a lot of processing time to perform some calculations. So at that point of time, you see the difference between just calculating covariance and correlation. For correlation, you have to extend and spend some more time to see the result or to process that particular data. When it comes to just covariance, you spend little processing time. So it depends on the study that you're doing and the models that you're training. Um, it all depends to that. It all comes down to processing time at the end. Based on that, based on your requirement, you just have to decide if you want to study more about particular dimensions, and if you can compromise for processing time, you can go with correlation. And if you are interested only with the direction, you can improve the processing time with just going for covariance. Same with
Okay.
standard deviation and variance as well. So now it is as simple as that. Now, when you calculated covariance, you calculated with a particular formula, right? And now what you just have to do, you have to divide that with sigma x and sigma y. What is sigma x and sigma y?
Standard deviation of
Standard deviation.
Standard deviation. So sigma x square denotes covariance. When you apply square root on,
variance.
variance. When you apply square root on variance, you will get standard deviation, right? So you will calculate standard deviation along x-axis, standard deviation along y-axis, and also covariance. Covariance, what does covariance gives us? What does covariance tells us?
Positive or negative or zero.
That relationship between two random variables.
Standard variables, positive or negative.
Yeah. So now do the calculation on your own and tell me what is the correlation value. Just apply these formulas. Now tell me what is the formula of sigma x. How do we calculate the standard deviation along x-axis? What is the formula for that?
Square root of 1 by n summation of xi minus mu whole square.
Summation of xi minus mu
Mu.
whole square. What is mu here?
Mean.
Mu is the mean. Now, if you want to calculate sigma y, Madhu, how do we calculate sigma y? psi sigma y.
In place of xi, we need to keep yi.
Yeah. So sigma I, we just have to we are calculating around the y points on y dimension. So it becomes yi minus mu whole square. So you apply this formula for sigma x and sigma y, you will get sigma x and sigma y. Now what is the value of covariance of x comma y? Kranti? Covariance of x comma y. Chintu?
1 by n summation of I is equal to 1 to n xi minus x bar into yi minus y bar.
What is x bar and y bar?
Mean.
Mean of the data points.
The data points.
Now, so only I need the values for these three things. What is the covariance of x comma y? What is sigma x? And what is sigma y? Everyone, you calculate from your side, and Wali just calculate these values and let me know. Apply these formulas, calculate these values, and then you can apply this particular formula to get the correlation value. So that is how you calculate the determinant of a matrix. It is always like alternatively you will get positive and negative. So the reason being you will take -1 whole to the power of I plus j. I plus j would be the row and column of that particular element a11. When you say a11, 1 plus 1 would become 2. -1 whole to the power of 2 would be 1. And then take the rest of the elements. So that is how actually it actually goes. This is just the form. This is just the way of calculating the determinant of a matrix. You all have gone through this in your first year, right? First year of engineering, calculating the determinant of a matrix. Even in intermediate, you will say this.
Yes, yes.
Yeah, yes.
You all know this, right? Calculating determinant of a matrix.
Yeah, one.
Okay. So never ever you will do the calculations when you're actually coding the stuff. You will have simple call methods to do all these things, but just you have to know at least the basic knowledge of calculating the determinant so that you can understand the concepts much better. Because you can use some sample data and do the calculations. So this is how we calculate the determinant of a matrix. And then these are very important. Understanding eigenvalues and eigenvectors. So this slide is for eigenvalues and this slide is for eigenvectors. So calculating the eigenvalues and eigenvectors for a matrix is really very important because these are core for dimensionality reduction. That's what we are going to learn later. So you should know how do we calculate eigenvalues and what eigenvalues actually tells us. Okay, so first let's understand how do we calculate the eigenvalues for a given matrix. Let's suppose a matrix A is given to you and you are asked to calculate the eigenvalues of this matrix. So if you are asked to calculate the eigenvalues of this matrix, this is what you have to apply. When you calculate the determinant of A minus lambda I, what is I?
Identity matrix.
Identity matrix. What is identity matrix? How does that look like?
1 0
0
0
0
0
1 0 0
So
0
for
1.
3 dimension, for 3 by 3, it would be 1 0 0 0 1 0
1 0.
and 0 0 1. Okay, so that is what identity matrix is. You have to do A minus lambda I. Okay, so and you solve the lambda. The values of lambda will give you the eigenvalues for this particular matrix. Okay, so once you calculated the eigenvalues, you can understand what eigenvalue actually means is. Okay, so here is the example. So I was given a matrix A. This is my matrix A minus lambda, and I'm applying I. So when I do that, minus lambda multiplied with this matrix, so it becomes 2 minus lambda, 0 minus 0, 0 minus 0. So this, it turns out to be this matrix, right? You know this, right? It's just like lambda. This becomes lambda, lambda, lambda. And minus will remain the same. So 2 minus lambda, 2 minus 0, 0, 0, I mean 0 minus 0, 0, 0 minus 0, 0. So and then becomes 0 minus 0, 4 minus lambda, right? And 5 minus 0, it would be 5. So you will just subtract these two matrices and then find out the determinant of this matrix. How do we find out the determinant of the matrix? The formula is just this. So this value into the remaining, the determinant of this. The determinant of the 2 by 2 is just AD minus BC, right? And now the rest would be zeros, zeros. So you don't actually bother about them. Now when you solve the roots of this lambda, those lambda values will give you the eigenvalues of this matrix. Okay, so when you solve this, 2 minus lambda is equal to 0. So lambda will become 2. So 2 is the eigenvalue of this matrix A. And if you calculate this, 4 minus lambda into 3 minus lambda minus 5 fours are 20 is equal to 0. Okay, just calculate the roots of this. What it would be? 12. 4 3s are 12. Sorry. 4 3s are 12 minus 4 lambda minus 3 lambda plus lambda square minus 20 is equal to 0. So this becomes lambda square minus 7 lambda, 20 minus 8, 12, 20 minus 20 plus 12 is 8. So this becomes lambda square minus 8x minus 8 lambda plus lambda minus 8 is equal to 0, right? So lambda, take the lambda common, lambda minus 8 plus lambda minus 8 is equal to 0. So now what does this becomes? Lambda plus 1 into lambda minus 8, right? This becomes lambda plus 1 into lambda minus 8. So lambda will become 8 comma minus 1 comma 2. So these are called as the eigenvalues of the matrix A. Okay. Are you clear with calculating the eigenvalues of a matrix?
Yes.
Okay. Now, you just don't stress more on this, but you will understand after the next slide. Eigenvalues actually tells us how much a matrix stretches or compresses in a particular direction. Okay, what is that direction and all, you will just understand. Let's come back to this later, but eigenvalues just tells us the stretch or compress in a particular direction. If you just take the example of an rubber, when you stretch that particular rubber, it extend, the length got extended, right? Will get extended. And if you just bring back that particular rubber to its old state, or if you just squeeze it, what happens? The length of that particular ribbon will actually reduce. So that is what eigenvalue actually will do. It actually increases, stretches the matrix or compresses the matrix. What does that actually means is what you can actually understand after the next slide. Now, how do we calculate the eigenvectors for a particular matrix? What does eigenvalues actually means is, eigenvalues indicates the direction that remains unchanged during the transformation. So eigenvectors indicates the direction Vectors actually will have magnitude and direction, right? So eigenvector, it's a vector which indicates direction that remains unchanged during the transformation. They may get stretched out, but don't rotate. Okay. So that is what eigenvectors actually do. When you calculate the eigenvectors of a particular matrix, the output would be few vectors. What those vectors will indicate? Those vectors will indicate that those directions are constant. That remains unchanged. Direction would remain unchanged during the transformation. When you transform the matrix with that particular eigenvector, that matrix will transform to that particular direction. It will not change the direction when you actually perform the transformation. Okay. So let's understand what is matrix transformation means is with a simple example. So let's understand what matrix transformation is. If I take the example of this matrix 2 comma 1 comma 3 comma 2. Okay, so this is my matrix. If I represent this matrix, how does it look like? On an xy axis. So let's suppose this is 1, 2, and 3. On my x-axis, this is 1, 2, 3 on my y-axis. If I represent these points 2 comma 1 is my point, this point, and 3 comma 2 is my this point. Okay, so these are my points on my when I represent this matrix with this on a two-dimensional space. Now if I transform this matrix, transform means it can be rotation or shifting from one place to other place. Let's suppose if I minus this with 1 comma 1, 1 1 1 1, what happens? All the points will just shift towards right. All the points will move towards this direction, right? So that is a transformation on the matrix. Understood? Transformation is just, it can be rotation or it can be movement of the points from one space to the other space, whatever it is. So subtraction is one sort of transformation on this matrix, transformation applied on this matrix. If it is plus, what happens? These points will move towards this, right? Understood? What we do plus, what is the transform matrix when we do plus? It would be 3, 2, 4, 3, right? What is 3, 2? This would be 3, 2. Let me just draw the diagram. 1, 2, 3, 1, 2, and 3. What is 3, 2? 3, 2 is just this point. What is 4, 3? 4, 3 is just 3 point. So this matrix transformed to this. I mean, it moved towards the right side. So this came here, this came here, right? That is what this matrix is. That is what this 2D representation is. So similarly, when you do minus on this matrix, what happens? These points will just move towards this direction, right? That is what matrix transformation is. And now if you multiply these points, what happens? That is also a transformation, but you just have to understand what happens if you multiply the points. I will take the other matrix again, a simple matrix. Let me take 1, 2, 3, and 4. This is my matrix. And I want to multiply this matrix with, this is 2 comma 2, right? This is 2 comma 2. So if I have to multiply this matrix, what I just have to do, it has to be 2 comma any dimension. Let me take 2 comma 1. So I'll take 1 and 0. Okay. Now I'm trying to transform this matrix by multiplying with a particular vector. A vector cardinal form representation is this, right? A vector can be represented in cardinal form in this way. So I'm now converting a matrix. I'm multiplying the matrix with a vector. Now what happens if I calculate this? It will be 2 comma 1. The resultant matrices will be 2 comma 1. So this is 2 comma 1. And now, so if I calculate this, what happens? 1 comma 1 is equal to 1. 1 comma 1 into 1 plus 2 comma 0. So this will be 1. 3 into 1 plus 4 comma 0 would be 3. So the matrix got transformed as a vector in this direction. Okay. So that is what transformation is. So now come back here. Eigenvector indicates the direction that remains unchanged during the transformation. So the direction of the resultant, once you transform the matrix with a vector, the direction of this matrix will remain unchanged. And that direction would be the direction of this eigenvector. Understood? The only thing is they may get stretched, but don't rotate. When a vector rotates, what happens? The direction changes. When it doesn't rotate, the direction of that vector doesn't change, right? So let's suppose if I take a vector something like this. This is my vector. If I move this vector in something like this, then what happens? The direction got changed. Direction is nothing but to which, the angle from some axis is the direction, right? So the direction got changed. But when I move the vector, when I stretch the vector, the direction will not change. When I string the vector also, it doesn't change. The only thing is it is just stretching or getting compressed, but the direction of this vector is not changing. Such kind of vectors are called as eigenvectors. When we transform the vector, when you do perform transformation on eigenvector, so the direction of that vector will not change, but it may get stretched or compressed. So you look at this lambda. Lambda is just a stretching or compressing parameter. So if I say 2 into 1 comma 3, when I multiply this, what happens? The vector will get stretched. The point here will just go here, that's all. But the direction will always remains the same. Understood? Let's suppose I take the point 1 comma 1, multiply this with 2, it becomes 2 comma 2. But it will always lie in the same line. The direction will always remains the same. So this multiplication factor would be just a stretching or compression factor. If it is minus 2, this becomes minus 2 comma 2, but it again didn't change the direction, but it just compressed in the other direction. Understood? That is what transformation means. When you transform any matrix, the direction of the resultant will remain unchanged, except that they may get stretched or rotated. They may get stretched, but they do not rotate. That is what eigenvectors actually means is. So to calculate the eigenvectors, what you just have to do is you have to apply this formula. This formula itself says when you transform any matrix with the eigenvector, V is the eigenvector, the resultant would always be eigenvector with a stretch parameter. So lambda is just the stretch parameter. It can stretch or compress. Lambda is the eigenvector. That is why I'm saying eigenvector tells us how much a matrix stretches or compresses in a particular direction. So from this formula, you can say that lambda is is a constant that specifies the stretch or compression of the matrix transformed. So A, when multiplied with the eigenvector V, the resultant will again be an eigenvector with a constant multiplied for it. Lambda eigenvector will always be a constant. It cannot be a vector. So that means like the vector is getting just stretched or compressed, but the direction is always remaining the same. So this vector and this vector is same. So the direction will always be the same. The direction will always be in the eigenvector's direction. That is what eigenvectors actually means is. Have you got that? Is that confusing or what? Hello?
Okay.
Yeah, I understood.
Follow the
Others?
direction.
Direction is towards which the point is When you are studying vector, you are saying this, right? Let's suppose if I have taken vector 1 comma 2, this is the magnitude and this is the direction. So this length is the magnitude and the direction is this is the direction of that particular vector. This is it, the vector is pointing towards this. That is what the direction is.
Yeah. Okay.
Is that clear for everyone? Do you want me to repeat this again?
Understood, mom. Not needed.
Okay. So now to calculate the eigenvectors. So what should I do? You know this, right? This is a right angle triangle. Okay. If I convert this to vectors, so this is vector A, this is vector B, and this would be the resultant vector C. If I want to calculate the direction of this vector with this particular vector, what is the formula for this? Theta is equal to tan inverse of B by A, right? That gives the angle or the direction of this particular vector. So similarly, you can calculate the direction of this vector from this particular x-axis. So as I said, 1 comma 1, 2 comma 2 will always have the same direction, but it got just stretched because this angle would be the same as this angle. So the angle remains unchanged. What eigenvector will actually do is when we apply transformation with the eigenvector, the resultant vector will have the same direction as the eigenvector. So this formula says that. So eigenvectors are same. The direction when you apply transformation is just multiplication. On multiplication is also transformation. So when you apply transformation on matrix A by using the eigenvector, the resultant vector will always be in the same direction because it is just the eigenvector with a lambda. Lambda is a stretch parameter. Whether it is stretching or compression, it just moves the point here and there. That's all. That is what actually eigenvector is. Thus, to keep it simple, eigenvectors are the directions in which the transformation will remain, the direction of the transformation will remain unchanged. That is what it is. So if you look at this example, you will get an understanding. So this is my, this is my matrix, and I'm trying to find out the eigenvectors for this. To get the eigenvector V, this is what you have to do. Eigenvector actually looks like this: x comma y comma z. Okay, so x comma y comma z minus x comma y comma z, because this is a matrix of 3 by 3, so this always has to be 3 by 1, then only the multiplication is possible. 3 comma 1, right? So this is what, so minus 1 is the eigenvector of this matrix. Where did we calculated the eigenvectors? In the previous slide we calculated the eigenvectors, right? For 2 comma 0 comma 0, 0 comma 4 comma 3, 0 comma 4 comma 5 and 3. What are the eigenvectors? I mean eigenvalues. 8 minus 1 and 2 are the eigenvectors. I mean eigenvalues. So we apply one after the other. We apply eigenvalues one after the other. First apply minus 1 and then apply 2 and apply 3. So that you get 3 eigenvectors for that particular matrix. Now I'm calculating with minus 1. So lambda is equal to minus 1 and this is eigenvector. So if you multiply it, the equations will become like this: 2x equal to minus x, So if you multiply this, what happens? It becomes 2x, 4y plus 5z, 4y plus 3z. So this would become equal to this. And if you break that, 2x is equal to minus x, 4y plus 5z is equal to minus y, 4y plus 3z is equal to minus z. And if you solve these equations, so if you solve this, this becomes x is equal to 0. And if you solve these two equations, you will get y equal to minus z. So when you take y equal to 1, z will become minus 1. Okay. So that is how the eigenvector is calculated. Now this is one of my eigenvectors. So now if I transform matrix A with this eigenvector, what happens? Look at the result of this. Result when I transform this matrix A with eigenvector, which is 0, 1, minus 1. If I multiply this with 0, 1, minus 1, I am transforming this matrix. Eigenvectors indicates the direction that remains unchanged. This indicates a direction that remains unchanged during transformation. During transformation, it will result into a vector whose direction remains unchanged. That direction will always be equal to the direction of the eigenvector, but you will have a parameter called as eigenvalue, which tells you the stretch parameter, whether the resultant vector will get stretched or compressed, will be given by the value which is lambda or the eigenvalue. So if I multiply this, let's see what happens. So if I multiply that, what will be the resultant matrix? If I multiply that, what will be the resultant matrix? So 2 into 0 is 0, 0 into minus 1, 0 into 1 is 0, 0 into minus 1 is 0. Okay, and then 0 into 0 is 0, 4 into 1 is 4, plus 5 into minus 1 is minus 5. So that becomes minus 1. And 0 into 0 is 0, 4 into 1 is 1, minus 3, which is equal to 1. Now if I apply lambda is equal to 1, this becomes plus and this becomes minus. So now look at this. Both the vectors are same, but it got compressed by minus 1. So minus 1 is just the eigenvalue, right? That is what we have got. Minus 1 is one of the eigenvalues. So eigenvector represents the direction which remains unchanged. When you try to transform any matrix with eigenvector, that matrix will be transformed into this direction. Okay, so let's suppose this is my point base. When you transform this with eigenvectors, and if the eigenvector's direction is this, these points will be transformed to this direction. Okay, so you're rotating the points from this space to eigenvector space. That is what it basically means. So you can consider these as different vectors. And now what happened? These vectors which are in different directions got transformed to this direction. So they all brought to this direction. So the resultant vector of all of them would be the eigenvector's direction. That is what actually the intuition behind this is. So when you transform any matrix with an eigenvector, the resultant would be the same. The resultant direction would remain unchanged. Remains unchanged means that direction would be same as the eigenvector's direction. But there will be some multiplication factor, and that multiplication factor specifies the resultant vector got stretched or compressed. So the resultant vector is stretched or compressed is what it actually specifies, but it always remains in this direction. Understood? Eigenvalues and eigenvectors.
Okay.
Everyone? Now let's hear from everyone, and what they understood is what I just want to hear. Let's repeat the same way about how we have done for what is that, probability distribution. Same way, let's hear from everyone about you know, what are eigenvalues and eigenvectors and intuition behind it. That is what basically eigenvectors actually means is, so you're transforming a matrix to a direction, which to the direction of the eigenvector. It is just means you're moving the points from one axis to, or one space to the other space. The new space is eigenvector space. So the points on this is the points of on x and y axis. This is matrix CA points. And now if you find out the direction of the points which remains unchanged of this data set, it would be something like this. That will be given by the eigenvectors. Now you will make these eigenvectors direction or eigenvectors direction as the principal axes. So the most variance axis is the principal axis, and the less variance is the axis is the, I mean, if you look at these points, stretch is more here. So the variance is more here. So the lambda value, the stretch of those data points, which is given by the lambda value, will be more here. I mean, the eigenvalue will be more in this direction. So I'll make that direction as principal axis and the other direction as minor axis. So I'll transform these points to this dimensionality. So the points will look something like this when you do the transformation using that eigenvectors. So you are just moving the dimensionality to the other side. You're making, I mean, you're creating new dimensions. So these dimensions are the eigenvector dimensions. Axes, eigenvector axes. Transforming from x-axis, y-axis to new axis, which is principal axis and the minor axis. Principal axis is nothing but the vector with highest eigenvalue. So here you have three eigenvalues, right? 8, -1, 2. So 8 will have one eigenvector, 2 will have one eigenvector, and -1 will have eigenvector. So if you calculate the eigenvector using the highest value of the if using the highest eigenvalue, you will get the principal axis. So that would be the most, I mean, that in that direction we will have more stretch and the points will be spread more. Okay, and when you have less eigenvalue, that will be that in that direction the stretch would be the more. That would be the eigenvector direction. The direction of that eigenvector would be the direction where the stretch would be less. Is that clear? Okay, let's go back to the next slide, which is positive semi-definite matrix. So a matrix A is called positive semi-definite matrix if for any non-zero vector x, the resultant of the quadratic from x transpose A into x is non-negative. So for a matrix A to be positive semi-definite, given a matrix A, it is called positive semi-definite matrix if this is satisfied. Then we can say a matrix A is called as positive semi-definite matrix. Okay, covariance matrix, you haven't encountered that, but you'll come later. So such kind of matrices are called as positive semi-definite matrix. So to just a simple example, if you take any vector, something like 1, 2, 3 is a vector. Okay, and you take a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is 3 by 3, and for this to get multiplied, it has to be 1 by 3. I'm saying x as a vector means it will be just it will have just one column when you represent this in cardinal form. So this would be 3 into 1. So when you multiply this, what happens? 3 into 3, 3, 3 into 3, 3. So 3. So finally you'll get a single value, which is 1 by 1, a constant value. So that has to be greater than 0. So you have to take x transpose here. This is 3 into 1, right? you have to take transpose. So that becomes 1, 2, 3. So finally, you're multiplying X transpose with A. And then the resultant will be multiplied with X. Again, X is just the a vector 1, 2, 3. So what happens? This is 1 into 3, right? And this is 3 into 3. What is the resultant matrix? 1 into 3 is the resultant matrix. And the final X is 3 into 1. So when you multiply these two matrices, 3, 3 would cancel and it would be just 1, a single constant value. So when that value is greater than 0, you can say the value the matrix A is called as positive semi-different matrix. What does this means is like the means that matrix doesn't shrink vectors too much or flip them over as a negative definite matrix. So a positive semi-definite matrix, when it is multiplied with any of the vector, when it is transformed, it will not shrink the vector so much. What does basically the transformation will do? It will rotate or shrink, right? So when it is a positive semi-definite matrix, it doesn't shrink the vectors too much or flip them over as a negative, because it is always greater than or equal to 0. So it will not just stretch, or it will depending on this value, the vectors will get stretched when we transform with this vector A, but they will not go to the negative axis. It cannot be negative. When it is negative, the direction will be flipped. It goes into the negative direction. That is what actually X transpose A into X greater than or equal to 0 means. So such kind of matrices is called as positive semi-definite matrix.
Chintu is in waiting room. Can you allow him?
Oh. Okay. That is what positive semi-definite matrix is. Take any matrix, and if you multiply, when you apply the vector onto that matrix, so the quadratic form, which is X transpose A into X, value should always be greater than or equal to 0. When you do that, when you are getting that, you can call that matrix as positive semi-definite matrix. So quadratic form, this the expression X transpose A into X is called a quadratic form of a matrix A with respect to the vector X. So we call this expression as quadratic form of matrix A with vector X. In simple words, it takes the matrix A and a vector X and measures how much this matrix stretches or compresses the vector. What is the influence of this vector on this vector of this matrix on these vectors? So if it is going to be a negative value, you cannot call this matrix as positive semi-definite matrix. And if this quadratic form value is greater than or equal to 0, we call that as positive semi-definite matrix. If A is positive semi-definite matrix, the quadratic form is always 0 or positive for any vector X. If it is 0, the matrix doesn't affect the vector's length. If it is positive, the matrix scales the vector without flipping it. Okay, so when the value of this quadratic form is 0, it will not show any effect on the vector's length. If it is positive, it just stretches it. It is all known. That is what transformation actually means. It may stretch or does not stretch, but if it is a positive semi-definite matrix, it will never flip the vector into the opposite direction. That such kind of matrices are called as positive semi-definite matrices. Okay. Now the properties of positive semi-definite matrix is eigenvalues of such matrix are always positive and real. Eigenvectors can never be negative for a positive semi-definite matrix. Okay, when you calculate the eigenvalues of this matrix A, they will always be real and positive. Those are the properties of positive semi-definite matrix. So, eigenvalues actually what eigenvalues tells? Eigenvalues tells us the stretch of the vector, right? Stretch of the direction of the resultant vector. So if it is negative, what does that mean? It flips the vector in the opposite direction. But when the matrix is a semi-definite matrix, it will not flip the matrix, because X transpose A into X is always greater than or equal to 0, right? So it will not flip the matrix. So if it is flipping that matrix, if it is flipping that vector, it would be not a positive semi-definite matrix. If it is a positive semi-definite matrix, it should not flip the vector. So it should not flip means eigenvalue should always be positive and real. It cannot be negative eigenvectors. How much the matrix, this that is all tagged together. This property is crucial because eigenvalues indicate how the matrix scales vectors along certain directions. If it is a negative, it shows the scaling in the negative direction, which is not a criteria for positive semi-definite matrix. For a matrix to be positive semi-definite, none of its eigenvalues should be negative. If all the eigenvectors are strictly positive, the matrix is positive definite. That is one of the properties. A positive semi-definite matrix is often symmetric. What does symmetric means? A transpose is equal to A. This is one of the properties of positive semi-definite matrix. The matrix has to be symmetric. Quadratic form. The key property of positive semi-definite matrix is that quadratic form X transpose A into X is always greater than or equal to 0 for any vector X. This ensures that the matrix does not flip or distort vectors in a problematic way. So given a matrix, if you're asked to find out whether it is a positive semi-definite matrix or not, the first thing you have to do is you have to make sure it is a symmetric matrix. Symmetric matrix means A transpose is equal to A. So 1 0 0 0 1 0 0 0 1, which is identity matrix. Is this symmetric?
Yeah.
So this is symmetric matrix. So I was given a problem to find out whether this matrix is a positive semi-definite matrix or not. So the first property I have to check is A transpose is equal to A. Then I'll find out the eigenvalues of this vector, of this matrix. So when I found the eigenvalues of this matrix, I should always get, you know, positive values, non-negative values. And then you can take any vector, and when you transform this vector, I mean, when you multiply this with this particular matrix, you should always get greater than or equal to 0. Then you will say the matrix is, then it means matrix is positive semi-definite matrix. That is what it will be actually given to you. I can, that is how the problems will be given. Given a matrix, you just have to find out whether the matrix is positive semi-definite matrix or not. Okay. Let's go back to the next slide. And this is what covariance matrix is. Why we have studied about positive definite matrix, positive semi-definite matrix is covariance matrix is a positive semi-definite matrix. So then what are the properties that are applicable for this covariance matrix? I said covariance matrix is a positive semi-definite matrix. Then by default, you have to understand that the matrix is symmetric matrix, right? And the second property is the eigenvalues of this matrix will always be greater than or equal to, or always positive and real. And X transpose A into X will always be equal to, will always be greater than or equal to 0. So those three properties will be applied for this covariance matrix. So now let's understand what is covariance matrix is. Covariance matrix is a matrix that shows the covariance between different variables in a data set. So different variables in a data set. Still now, you just have seen the covariance, right? Covariance is just the behavior of the two random variables. How one random variable is making an impact on the other variable is what you have studied. Now you have n dimensions. You just have seen 2 dimensions. You have seen X and Y, smoking and health, something of that. When you have n dimensions, this is how the covariance will be calculated. The covariance of each dimension with the other dimensions will be calculated. X1, X2, X1, X3, so on, X1, Xn. And what is the covariance between X2 and X1, X2 and X2, X2 and X3, and all that stuff. So that is how the covariance matrix will always be calculated. Okay. And what it says, the covariance matrix is a matrix that shows the covariance between different variables in a data set. What are different variables? X1, X2, X3, all are different variables. It is a square matrix where each element represents the covariance between two random variables. So each value will give us the covariance between two random variables. The diagonal elements represent the variance of individual variables, and off-diagonal elements represents the covariance between pair of variables. What are diagonal elements? These are diagonal elements. Other than these elements, the other elements are called as off-diagonal elements. So diagonal elements represents the variance of individual variables. So this covariance x into x is nothing but the variance along x-axis, right? So covariance along x-axis. This is calculated by x minus mu whole square by the n. Sigma I is equal to 1 to n, right? So when x1, the both are same. Covariance is nothing but x minus x bar, y minus y bar. When x is y, it will be x minus x bar whole square, which is nothing but the covariance along the x1 axis, right? This is also the covariance along x2 axis, covariance along xn axis. I mean, variance. Covariance of x1 is nothing but the variance along x1 axis. Covariance along x2 x2 is nothing but the variance along x2 axis. But covariance along x1 x2 will be calculated by x1 minus x bar, y1 minus y bar. Here x1 and y1 are different. Y1 is nothing but the x2 here. X1 and x2 are different. But here x1 and x1 are same. So that becomes x1 minus x bar whole square, x1 minus y1 whole square. So this would be the x bar only because same points. So that becomes x1 minus x bar whole square, which is nothing but the variance along x-axis. Understood? That is how you calculate the variance. Variance and create the covariance matrix. Now you understand this, right? Covariance along x2, x1 is same as x1, x2. It is just nothing but x1 minus x bar into x2 minus x bar. If x1, x bar and y bar are the means. So it's same x2 minus y bar or x1 minus x bar. So the multiplication of these two is same, right? So these two values will always be the same. That is why covariance matrix is a symmetric matrix. A transpose is equal to A. That means even if this comes here or this goes here, there is these two values are basically same. So A transpose will always be equal to A here. That is why we can call the covariance matrix as symmetric matrix. The diagonal elements are the variances of the individual elements, which is like variance along xi. The off-diagonal elements are the covariance between pair of variables, covariance of xi, ij. You know how to calculate the covariances. So basically, covariance matrix is a matrix that shows the covariance between different variables in a data set. It is a square matrix and it is also a positive semi-definite matrix. It means like eigenvalues of this matrix will always be greater than or always be positive and real. And it is a symmetric matrix. And when you multiply this, when you get the quadratic form of this particular matrix, it will always be greater than or equal to 0. Okay. Given a set of n-dimensional data points, the covariance matrix sigma is an n by n matrix where the element of row I and column j is the covariance between the ith and jth variables. That is what covariance matrix is. It is just a representation of the covariances along different dimensions as a matrix when you have n dimensions. Clear? Are you understanding or it's getting difficult? Hello?
Yeah, able to understand.
Yeah, you're able to understand this. Okay. Now, um, now look at this diagram. The covariance matrix is symmetric, meaning covariance of x comma ij is equal to covariance of xj comma xi. The covariance matrix is positive semi-definite, meaning it will always have non-negative eigenvalues. Right? The covariance matrix is called as positive semi-definite. Covariance matrix is positive semi-definite matrix. So all the, you know, all the properties of positive semi-definite matrix will be applied to the covariance matrix as well. What are the properties of positive semi-definite matrix? A matrix has to be symmetric. A matrix has to be the eigenvalues of that matrix always has to be positive and real. And also, what is the third one? X transpose A into X should always be greater than or equal to 0. X can be any vector. Okay. Now, given these data points, these are the data points given, you have to calculate the covariance matrix of this particular matrix. So how many dimensions you have?
Two.
How many points you have?
5.
5 points. So when you have 2 dimensions, what is the covariance matrix? How does a covariance matrix looks like? When you have 2 dimensions, x comma y, someone has to Kranti. Uh, you have to go on mute. So I don't hear my voice back. Okay, so when you have 2 dimensions, what this specifies is the matrix will always be 2 by 2 matrix. So number of dimensions into number of dimensions. So because now you have to find out the covariance variance along x-axis, and this would be variance along y-axis, and this would be the covariance along x and y-axis, and this value will be same as this value. Now, can you calculate? How do you calculate the variance along x-axis? What is the formula?
One by n into summation of xi minus mu whole square.
Summation of xi minus mu whole square.
Whole
That is
square.
how you calculate the variance. So when you get that value, you have to place here. And when you calculate the variance along y-axis, you have to place that here. And when you get the covariance along these two axes, you have to place it here and here. That forms the covariance matrix. Once you got the covariance matrix, you can also find out whether that is symmetric or not. To validate that as a positive semi-different matrix, you have to get these three properties satisfied. Eigenvalues of that matrix has to be positive and real, and multiply that with any vector so that the resultant vector, the resultant value should always be greater than or equal to 0. Can you calculate the covariances, and get the what is that? Oh, get the covariance matrix for that data. 1, 2, 2, 3, 3, 4.
Variance along x-axis is 2 and variance along y-axis is 2.
Okay, so variance along x-axis is 2, variance along y-axis is 2. Now we have to find out covariance between the two spaces.
Yeah, even those are twos.
So those are 2. So this is how the covariance matrices will be represented. 2, 2, 2, 2. So now we got the covariance matrix. Is everyone able to complete the calculation? Understood how this is calculated?
Yeah.
Everyone?
Yes.
Everyone did the calculation right now. Uh, can you tell me, can you do the calculation? I mean, can you find out whether that the one which you got now is positive semi-definite or not? Valli, Madhu, Chintu, have you completed that?
I
Sai?
got 2, 2, 2, 2.
So now I just want to understand if this is positive covariance, I mean positive semi-definite matrix or not. So the first thing that I can do is um, uh, uh, is this a symmetric matrix? A transpose is equal to A
Yes.
property of symmetric matrix. So this is a symmetric matrix. The first property is satisfied. The second property is finding out the eigenvalues for this. To find out the eigenvalues, what I have to do? I just have to do A minus lambda I is equal to 0. The determinant of A minus lambda is equal to 0. So this becomes 2 minus lambda, 2, 2, 2 minus lambda, right? So now this becomes 2 minus lambda whole square minus 4 is equal to 0. So 2 minus lambda becomes 2. So lambda would become 0, right? So that is the value of lambda, right?
We can have lambda as minus 2 as it, right?
Lambda is
Minus 2.
square root of 2 is plus or minus 2. That's what you're saying.
Yeah, yes, yes.
Lambda has 2 values now. One value is 0, one value is. Oh,
It would be 4, right?
two
No,
values,
it would be
two
minus 2, right?
eigenvalues.
Minus.
So 2 minus lambda is equal to plus or minus 2, right?
Mm-hmm.
So lambda will become 2 plus or minus 2, right?
0 and 4.
So that becomes 0 comma 4, right?
Okay.
Yeah, 2 values.
So
Yeah, correct.
lambda, the
Sorry.
eigenvalues are always positive and real. And now if I multiply this matrix with any vector, what you have to get? You have to get um, greater
Greater
than or
than
equal to 0. So now my vector is 2 comma, the matrix is 2 comma 2. I take a vector which is minus 1, minus 1. You can take any vector, that's your wish. But for now, I'm taking minus 1 and minus 1. So this becomes, what this becomes? It becomes minus 4 and minus 4. Because minus 1 into 2 is minus 2, minus 1 into 2 is minus 2, minus 2 would become minus 4. And the same applies for minus 4. When I multiply this with minus 1 and minus 1, this becomes 4 plus 4, which is equal to 8. Right? This is greater than or equal to 0. So the third property is satisfied. The first property is satisfied, second property is satisfied, and the third property is satisfied. And now let me take another example, minus 1 and 1. This is another vector I am taking. 2, 2, 2, 2, and the other vector is minus 1 and 1. Now if I multiply this, this becomes 0, and this becomes 0, And when I multiply this with this, so this becomes equal to 0. So this is equal to greater than or equal to 0. So third property is also satisfied. So that is the reason we say covariance matrix is positive semi-definite matrix. That is the conclusion. Got it?
Yeah.
Right. So that is what positive semi-definite matrix. We have studied all this stuff just to understand positive semi-definite matrix. The reason being, you have to understand what positive semi-definite matrix is, then only you will understand why we called covariance matrix as positive semi-definite matrix. So what are the properties of positive semi-definite matrix?
A transpose is equal to A.
That means a matrix is symmetric.
A transpose X transpose into A into X is greater than or equal to 0.
What is X?
Any matrix,
Any vector. It would be just
any vector 1 into 1 vector.
yeah. What is the third property?
Third property,
Eigenvalues should be positive and real.
positive.
Yeah. So eigenvalues. So the reason why we understood why we gone here is you have to understand how to calculate the eigenvalues,
Positive
and
and
only you
real.
will be able to calculate the eigenvalues for the covariance matrix. So then when you get the eigenvalues, you will understand whether they are positive or negative. And then eigenvectors, you will shortly understand why we studied about that. What is that? Eigenvectors. But for now, let's go back and understood what is normal distribution. Okay. What is normal distribution? We already studied about normal distribution, right? Normal distribution is a probability distribution. What is probability distribution? What is probability distribution?
It describes how
The
the
value
probabilities are spread across for a random variable.
Yeah. How the probabilities of a random variable are spread is what probability distribution basically describes. Okay. Normal distribution is a probability distribution. That means how the points of a random variable are spread. That describes how the values of the variables are spread. It is also known as Gaussian distribution because this is invented by Gaussian. Under his name, this is also called as Gaussian distribution. The shape of this distribution is a bell curve. Most values cluster around the mean and fewer values occurs as they move away from the mean. So for a normal distribution, the best example is this is the normal distribution example. So this is how the curve of a normal distribution will look like. So what is this saying? Most of the values cluster around the mean. So this is the mean of this normal distribution. So if you take the example of the students in a class, most of the students marks will fall around the mean. Okay. Very few students will have high marks and very few students will have very high marks. So the high marks number of students who are getting high marks will be less than average number of students who got average marks, and number of students who got very high marks is much lesser than the number of students who got very higher marks. The same applies for low marks as well. So every distribution, most of the data that we see in the real world falls into normal distribution. And this is very important and will be very interesting. You can take the example of anything, marks of the students in a class, height of the students in a class. It can be anything, shoe size of some population. Everything falls under normal distribution. So what are the characteristics of a normal distribution is the distribution is symmetric around the mean. What does symmetric means? If you flip, it always looks the same. If this is the mean, if you fold this around the mean, like if you fold both of them this way, they will actually collide with each other. That is what symmetric means. It looks like same on both sides of the mean. So this is the mean. Okay. Bell shape, the peak is at the mean. So the highest value of the distribution will be at the mean. And the tail taper off as you move away from the center. So when you move away from the mean, the tail will comes down close to 0. Okay, in normal distribution, it never be equal to 0. Even when you go to infinity, that will be very less, but it will not touch the axis. That is something which you have to understand. Mean, mode, and median. What are these three? These three are central tendency measures, right? All of them will be same for the normal distribution. All are same and located at the center for the normal distribution. So that is what normal distribution is. Normal distribution looks like this, and it will be, the value will be high at the mean, the peak. The value of this normal distribution will be peak at the mean. And when we move away from the mean, the values will gradually decrease. And when we move towards the mean, it will be increased. So is this a continuous distribution or a discrete distribution? I mean to say, is that continuous random variable or discrete random variable? What is the difference between discrete random variable and continuous random variable? How do you calculate the probability of a continuous random variable?
This is a continuous random variable, and we calculate it based on the probability mass function.
Okay.
So
Probability
based on the
mass function
range,
is for
like a
continuous.
range. Yeah, it is for continuous. Sorry, probability density function.
Yes. So how do we calculate in probability density function? The probability of taking any value of a continuous random variable is?
We just integrate it over the function.
No,
The
we
limits should
integrate over
range.
the range to get the probability
Yeah,
density.
sorry, range.
What I'm asking is, what is the probability density function? What is the probability of getting any value of a continuous random variable? It is 0, right? Probability of getting any value in a continuous random variable is 0.
Yes, correct.
And what is
Because the
probability
value
mass
should be
function?
continuous, correct?
What is probability
Probability,
mass function?
it is calculated at each and every level, like discrete values.
Yeah,
So
it is.
suppose we have 1, 2, 3, 4, 5, we'll calculate it each and every interval, and we get the same probability for each of them.
Yeah. So that is what. So this is a continuous random variable. So when you want to calculate the probability of the random variable taking the range of values, like probability of, how can we, let's suppose this is A and this is B. If you say probability of random variable taking the value within this range, how do you calculate this? This is just the integration between A to B and the random variable, right? Integrating the probability density function in this range. That is how you calculate the probability, right?
Yeah, correct.
Yeah. So have we discussed about the formula for normal distribution earlier? No. This one.
No,
Okay.
we
So
haven't.
this is the probability density function for a normally distributed data set. If the data set is normally distributed, if you want to calculate the probability density function, okay, this is the formula 1 by root of 2 pi sigma e to the power of minus x minus mu whole square by the 2 into sigma square. This is the mu of the normal distribution. Sigma is the standard deviation of the normal distribution. Okay. And if you want to calculate the probability distribution from around A to B, this is the formula. You just have to integrate, find out the area in this under this probability density function. So if you have to find out the area under this function, you just have to integrate the function from A to B, right? You just have to apply the integration for this particular probability density function. Got it? So this is how, in most of the cases, this is how it looks like. So this is the mu, and this is one standard deviation. and this is 2 standard deviation, and this is 3 standard deviation. And this is 1 standard deviation in the other direction, 2 standard deviation, 3 standard deviation. Okay. And it is said that in most of the normal distributions, 68.2, okay, there is a rule called as 68. Okay, so look at this. 68% of the data points fall within 1 standard deviation. So from mean, if you go 1 standard deviation, you will have 68% of the data. Okay, and when you go to 2 standard deviations, you will get 95% of the data. Okay, what does 68 plus 26 looks like? 68 plus 26, it would be 94, right? Plus 0.5, which would be 95%. So 95% of the data resides within 2 normal deviations. And within 3 normal deviations, 99% of data will reside. So 95 plus 2.1, 2.1, which is 99.2. Okay, so if you basically add all this, so that becomes 34.1, 13.6, 2.1, which is 8.456,789, 49.8 into 2. 8 into 2. So 6, 192. This is 99.6. So it is 99.7% of data resides within 3 standard deviations. So the rest of the data will reside away from 3 standard deviations. So that is how the normal distribution basically, normal distribution data will be distributed. So 68% of the data points will reside within 1 standard deviation, 95% of the data resides within 2 standard deviations, and 99.7% of data points will reside within 3 standard deviations. So we will just study the study up to 3 standard deviations to completely study about that sample. Okay. So it has many interesting facts that you're going to learn before, but this is how the probability density function will be calculated. What you will just do is integrate. If you want to find out the number of data points, the probability of a random variable taking a value within this range will be calculated just by integrating from this point to this point. So if I want to calculate the probability of a random variable falling within this range, I just have to calculate the area under this curve. So this curve, I just have to find the area under this curve. So what I just have to do, integrate from mu to sigma. So mu can be 5 and sigma can be 7. If it is sigma is equal to 1, so 5 plus 1, which is 6. So I have to integrate from 5 to 6. Okay. So there is a simplified form of getting this area under this normal distribution. We will get to know that later. But so you have to understand few things. What is 68, 95 and 99.7 rule? Okay. That is nothing but 68% of the data will fall within 1 standard deviation. What is standard deviation? The spread of data points, right, from the mean is what standard deviation is. So if you go 1 standard deviation away from the mean, you will find 66% of the points. Okay, sorry, 68% of the points. When you move 2 standard deviation away from the mean, you will find 95% of the data points. When you move 3 standard deviations away from the mean, you will get 99.7% of the data points. So that is what 68, 95 and 99.7 rule means. So if you look at this formula, you all know this. Mu is the mean, sigma is the standard deviation, sigma is the standard deviation, x is the value of the random variable. Okay, any value. So as you integrate from a to b, x can be a and b. You just have to apply minus. This is what normal distribution actually means is. Okay, and now go to the standard normal distribution. This is very important. This helps us to actually calculate most of the stuff under normal distribution very easily. Okay, now understand what is the difference between normal distribution and standard normal distribution. Standard normal distribution means the mean of the distribution is 0 and the standard deviation is 1. Okay. In the previous case, the mean is mu and the standard deviation is sigma. But when the mu is 0 and sigma is equal to 1, we call that as standard normal distribution. Such kind of distribution is called as standard normal distribution. So for this also 68% of the data falls within one standard deviation, 95% of data falls within two standard deviations, 99.7 data falls within three standard deviations, which we already know, which is 68, 95, 99.7% of data. But why standard normal distribution is very important is what we are going to understand now. Okay. Look at this. This would be very interesting and very important too. So just the definition here, the standard normal distribution is a special case of the normal distribution where the mean is 0 and the standard deviation is 1. So mean is 0 and standard deviation is 1. It is useful because it allows us to compare data from different normal distributions by converting values into Z scores. So we are converting the values into Z scores. Allows us to compare data from different normal distributions by converting values into Z scores. What does this mean is it can be any normal distribution. It can be any normal distribution. The mean can be 100, standard deviation can be 120. So we can convert such kind of normal distribution into this normal distribution. We can do that. Okay. So that is what it is useful because it allows us to compare data from different normal distributions by converting values into Z score. So we can convert this normal distribution into this normal distribution. That is what actually standard deviation is most helpful with. So you found this as a tedious task, right? If you want to find out the area under this particular curve, it's a tedious task. There is a lot of mathematics involved within this. But if you convert that to normal distribution, you have an Z score table. We call this table as Z score table. Okay, so if you want to find out the area under this particular curve, which is a standard normal distribution, okay, this curve is standard normal distribution and this table is applicable only for the distribution which is standard. That means mean is equal to 0 and standard deviation is 1. This table is applicable only for such kind of distributions. So how do we know the value or the area under the curve, area under the standard normal distribution curve from this table? Okay, it's as simple as this. So if you're getting the Z score is 0.57, okay, if you're getting the Z score is 0.57, so the area under that curve would be 0.7157. Okay, and the other important thing that you have to understand is the area under the normal distribution is always equal to 1. Okay, the area of the curve under normal distribution, if you calculate the area under this curve, it will always be equal to 1. Okay, so look at this. So if you know the total area under the curve is 1, right? And this table will gives us the area under the curve when Z is equal to 0.57. So when you are getting the Z score, how do we calculate the Z score and all? You will understand. I mean, we will shortly understand that. But let's just understand this. So how do we use Z score table to predict the area under the curve? So if I get the Z score as 0.57, if you go to this particular table, 0.57, this is 0.5 and this is 0.07. So the area under the curve would be 0.7157. So that would be the Z square. If that is the Z score. So this value of this particular area is 0.7157. That is what you can find it from the Z square table. Now, if you want to find out the area beyond this point, okay, if probability of Z score greater than 0.57 means, what do you have to do? You have to subtract this area from the 1 to get this particular area, because total area is 1. You know this area from the Z score table. To calculate this area, how do? You just subtract 1 minus area under this curve to get the area on the right side. Okay, that is how you calculate the area under the curve. Now you can convert back this to the Z score to find out the area under the curve between this thing. So I just wait for 2 minutes. You will see that example lively, how to convert a particular standard deviation to this standard deviation. But let's understand the different terminologies here. That is more important with this particular slide. So the Z score tells you how many standard deviations a value is from the mean. Z score tells you how many standard deviations a value is from the mean. If you have a particular value, if you want to find out, when you find out the z-score with that value, so if you're given a data set, you can calculate the z-score, right? For the standard normal distribution, what is mu? For standard normal distribution, what is mu?
0,
What is standard deviation?
1.
Okay, so z will always be equal to x, right? In standard normal distribution, but this would be different in normal distributions where mean is not equal to 0 and standard deviation is not equal to 1. When you say z score is 1.5, what does that mean is, when you say z score is 1.5, when you say z score is 1.5, it means we are 1.5 standard deviations away from the mean. Okay, that particular point is 1.5 standard deviations away from the mean. So look at this diagram. This is 0, right? This is the mean and the standard deviation. When we have 1.5, that means to say the data point is 1.5 standard deviations away from the mean. Okay, that is what z-score actually means is. As I told you, most z-scores will fall within the range of -3 to +3 because 99.7% of the data points are falling within that range. And here is the curve is symmetric around 0 for standard deviation. These are properties. The total area under the curve is 1. The random variable z varies from -infinity to +infinity. Okay. So now you understand what is z-score. Z-score just gives us how many standard deviations away from the mean a point is. A point is how many standard deviations away from the mean is something what z-score gives. So from the z-score table, you can calculate the area under the curve of a standard normal distribution. So if you want to calculate the other part, area of the other part, you just have to minus that from 1 because the total area is 1 and you know the area of this part. You just have to, when you want to get the area, when you want to find out the area of this part, you just have to subtract the area of this part from -1, which gives you the area under this part. Now, if you want to find out the area of a graph, something of that sort, this is let's suppose this is a standard normal distribution. If you want to find out the area under this curve, how do you find out? And here the z is 0.5, I would say. Here the z is 0.57, I would say. If you want to find out the probability of 0.5 less than x less than 0.57, how do you calculate the area under the curve? So you got this right. So this is how my graph looks like. This is my standard deviation. Sorry, this is my normal distribution. Now I just want to find out the area under this curve, under this particular area, which is 0.5, 0.57. These are my z-scores, 0.57 and 0.5. How do you calculate the area of this part? This part.
Z-score of 0.57 minus Z-score of 0.5.
Yeah, that's all. So if you want to find out the area under this part, what you will first, what is that you will do for the first time is, you will find out the area under the whole curve starting from here to here. Okay, so when you get the whole area, which is when you say 0.5, 0.07, it is 0.7157, right? 0.7157 is the area of this whole part. Now you have to subtract until 0.5. 0.5 value is this one, 0.6915 minus 0.6915. This value will give the probability of a random variable falling within this range, 0.5 to 0.57. It is just like that. If you are asked to find out the other part, rest of the part, You just have to minus 1 minus the area under this curve. That is how you actually manipulate the z-score value to find out the area under this curve. Now, the next thing that we have to understand is how to convert a normal distribution to standard normal distribution, and how to calculate the area of the standard area under the normal distribution back from the standard normal distribution is what you are going to learn now. So if I go back to this next slide, you have to understand, as I told you, any normal distribution can be converted to standard normal distribution. That process is called as standardization. What is standardization? Standardization is converting a normal distribution to a standard normal distribution. Converting a normal distribution to a standard normal distribution is called as standardization. This involves transforming the data so that it has mean of 0 and standard deviation of 1. This is done using the z-score formula. So let's not bother about how we are doing that. Let's just understand what is standardization. So this is one of the normal distributions where mu is 77.4 and standard deviation is 40.1. So I can convert the standard deviation to normal standard deviation. I can convert this normal distribution to standard normal distribution. I can convert this normal distribution to standard normal distribution. Any kind of normal distribution can be converted to standard normal distribution. That process is called as standardization. Okay. And once we have that normal distribution, standard normal distribution, you can calculate the area under any part using this z-score table. Okay. This is called as z-score table, and you can use this table to calculate the area under the curve. So that again, once you calculated the area under the curve, you can also go back and find out the area under this normal distribution using the z-score formulas. Now, how you can actually convert this graph to this graph and find out the area under this graph using the area under this graph is something what you can actually find out now. You will see now. So this is the example, and I have the standard deviation. This is the normal distribution that I have where mu is equal to 60 and standard deviation is equal to 10. Now, what I am going to do is, the main intention here is I want to calculate the area under the curve just read this. Suppose that we have gathered data from last year's final chemistry exam. We gathered data from last year's final chemistry exam and found that it followed a normal distribution. We know what normal distribution is, with a mean equal to 60 and standard deviation is 10. Okay, mean is given, standard deviation is given, and it is also said that the chemistry marks followed normal distribution. You know what a normal distribution is. What portion of students scored less than 49 of the exam? 49 of the exam. So you have to find out the probability of a random variable less than 49. Okay. What is random variable here? Random variable is just the chemistry exam marks of the students. They can take any value from 0 to 100, right? So now we want to calculate the probability of a student getting less than 49%. Now, technically, what you have to do, you have to find out this area. For that, you have to apply this 0 to 49, 1 by the root of 2 pi into sigma e to the power of minus x minus mu whole square by the 2 into sigma. That is the probability normal distribution, right? So this is the probability normal distribution, x minus mu whole square by the 2 into sigma square. So you just have to integrate from 0 to 49, and you have to find out the mean of this. Mean is given, standard deviation is given. Apply in this formula, x minus mu whole square into 2 into sigma square. Integrate this and you will get some value. So that is a tedious task. We all know integrating these exponentials, converting them into values is a tedious process. The simplest way is this one. The first step I would do is convert this normal distribution into standard normal distribution. You know, this is standard normal distribution because mean is equal to 0, standard deviation is equal to 1. How do we convert every point here into here? So there comes the z-score. What is the mean here? 60 is the mean. Apply that point 60 here. 60 minus 60 by 10. So that becomes 0. So 60 became 0. What does 70 became? 70 became 1. 80 became 2. 90 became 3. Similarly, 30, 40, 50 becomes minus 1, minus 2, minus 3. Now we converted every data point here to here. Okay. Now we also have to convert this point where we have to find out the area under the curve until 49. So I'm converting 49 also into z square. So 49 minus 60 by 10 would be 11 by 10, which is 1.1, right? 49 minus 60, what it would be? Minus 11 by 10, which will be minus 1.1. So now I have to find out the probability of curve until minus 1.1. Area under the curve until minus 1.1. Okay. So that is what it is. Now, what is the area under the curve for minus 1.1? So 0.1357. Okay. So the probability is 0.1357. That is the area under minus 1.1 curve. Now, the same can be applied. This is the answer for this. Okay. So the probability of student getting less than 49 is 0.1357. Got it? That is how you can use the standard normal distribution to calculate the areas very easily using the z-score table. Convert every normal distribution into standard normal distribution. And if you want to find out the probability, just use the z-score table, and that will give the area under the curve. That can go back to the answer for your question of your normal distribution. Understood? Understood? Hello?
Can you repeat once again how it got converted from normal to standard normal distribution?
Yeah, sure. It's as simple as this. So I have this, right? Look at this. This is my normal distribution, and these are my data set. These are my values, right? So now my intention is to convert this diagram to standard normal distribution. What is standard normal distribution? Standard normal distribution is nothing but mean is equal to 0 and standard deviation is equal to 1. Now, what I'm going to do here is take the value of 60, okay, and apply to the z-score. 60 minus 60 by 10 becomes
0.
so 0. So 60 becomes 0.
Okay.
Now 70 minus 60 by 10. That becomes 10 by 10, right? So 70 becomes 1 now. And 80 minus 60 by 10 would become 2. 90 minus this becomes 2. Now 50 becomes minus 1. 40 becomes minus 2. 30 becomes minus 3. Once we apply these values to this formula, get these values, right? Are we clear till here?
Yes, understood.
Right? Now 49 is again converted to this scale. We are just scaling using this z-score. So this graph is scaled to this, and this value is scaled to this. Now you can get this probability, which is area under this curve from z-score table, which is minus 1.1. So the area under the curve is 0.1357. So this becomes 0.1357. Now this goes here and falls here. The same value applies for this as well. That is how you calculate the area under the curve for any normal distribution by converting that to standard normal distribution.
Yeah,
Clear?
understood.
Okay. Everyone is able to follow or no?
Yeah.
Understood.
Able to follow.
Okay. So from tomorrow is like complete exercises we will do for all the concepts that we are going to learn. we will do some set of exercises. Set of exercises in the sense we will solve the manual problems. In our semesters, we will be given some. I'll just quickly show you. So on every concept that they teach, there we will have some exercises that we have to complete every day at our home. So we are going to solve those exercises starting tomorrow. I mean, for tomorrow, we will just do lecture for some time, and then we will try to solve 3 exercises. I'll quickly show you that. So this is one of the lectures, and inside this we will have some homeworks to do. Where is that? Assignments. Go back to assignments, and then we will have quizzes as well. You can also we can also do some quiz that is given over here, but I'll just show you an example of classroom activities. So that helps you to understand the concept much better. So this is one of the examples. Like this is what we are going to solve. Hide floating meeting. Okay. Go back here. This is the data set that is given. So data, attributes, and points. Consider the following data matrix. You know what is data matrix is. And from this, you have to understand what is the dimensionality of this data. What is the number of points in this data? Okay. What is the dimensionality of this data?
Rows.
What is the feature vector for data point x2? What are the attribute type for attributes average GPA? What is the attribute type of average GPA? What is the attribute type of level of execution? What is the level of education? What is the attribute type of measure? So this kind of exercises, now we are at we completed around 2 assignments. I guess we should be able to complete 2 assignments. So that is where we are right now. So let's tomorrow let's see. I'll just give one question to everyone so that how far we are with understanding the above concepts is what we will understood. Okay, so this is something that we are going to do as we move forward. I'll just pass these assignments to you, so you should be able to solve this over the weekend on a notes, and should be given back to me so that I can just go validate the things that you're doing. So that is something which that clarifies where you will solve more of these kind of examples in those assignments. So that's why I have shown you. And now the next thing is central limit theorem. This is also very important and very important to understand. And these are all interlinked. Now you find out what is normal distribution, and you found out what is standard normal distribution, and you also find out what is z-score, and you also find out how to calculate the area under the normal distribution easily by converting that to standard normal distribution. And now this is also an important theorem that tells you something about the data in the universe. Taken many random samples from a certain size from a population and calculate the mean for each sample. Okay, so understand this. This is also something which is important. So far, so good. Are you able to follow everything that we discussed? It is as simple as this. Don't leave the track if you don't find something, if you don't understand something. Let's suppose if you don't understand eigenvectors intuition that we discussed, go back to YouTube and get to know some animated videos. There will be some animated videos on understanding the eigenvectors intuition. So go search for it and go through 2 to 3 videos, and then you will get some clarity on it. So that is how you can better learn. If you don't understand some concept, just go to YouTube and just try to understand, try to see the animated videos. And if you are clear with that concept, just revise that. But try to be on the track. So these are all basics. And from the model, when you start understanding the models, or we call them as classification, clustering, regressions and all that stuff. Those all will be dependent on these concepts. So once you are clear with these concepts, you would be able to easily understand those concepts. Those calculations are much easier than these basics. So these are very important. I think from by today, end of the day, you will be done with all the basics. From next week onwards, you will start analyzing different data sets. I mean, analyzing the data in higher dimensions. Till this point, we are just seeing only 1 or 2 dimensions, right? But in real world, there will be so many dimensions or attributes that we want to analyze. From next week onwards, you will just go start doing the analysis on the actual machine learning data sets. I mean to say, just understand the intuition, not actually the coding part. But let's complete as much as we can today. So what is central limit theorem says is that central limit theorem, just try to read this. You will get an understanding out of this. Take many random samples of certain size from a population. You have some population. Population means all the data set. Take some samples out of it. You also know what a sample is, right? What is sample and what is population? What is population and what is sample?
Group of data
Population.
points.
Sample means we took that example. You remember elections in a particular state. Population means all the population in the state. Sample means take around few
Some
people
set of
from the set of people. Like if you take a village, if you have 100 voters in that particular village, out of the 100 voters, you pick 10 voters from that particular population. So that 10 voters will become the sample out of this population. So we understand the population parameters from the expected parameters. Okay. Or like from this sample, we will try to understand the population, right? That is what sample and population means. Like take many random samples, not one random sample out of this population, pick 10 samples and drop them, pick another 10 samples, drop them, pick another 10 samples. Okay. Likewise, take many random samples from the population and calculate the mean of each sample. Okay, you're taking different samples from the population, different n number of times, and you're calculating the mean of the population. The distribution of these sample means will be normally distributed. So those means are normally distributed if the population itself is not normally distributed. We don't care how the population is distributed. Any kind of distribution, it's a uniform distribution. The distribution can even look like this. So the distribution of the population can even look like this. But even for this distribution, if you take some samples and calculate the mean of these samples, though that mean will be normally distributed. That is what central limit theorem says. So this is just an intuition. And lastly, we can draw a histogram of that mean over here on the right. So this is the distribution. From this distribution, you have taken some samples. Okay. So if you don't understand this example, this data points, this is how you have to understand it. Okay. Let me just explain that diagram to you. So these data points will be represented by this particular graph. Okay, you call that as histogram. You first have to construct a histogram, and from that histogram, you will actually draw this diagram. So let me just explain you that so you can better understand this. So how does this graph coming is what you have to understand. How does this graph coming from these data points? So let's say these are the data points, right? They are overlapping. You're looking at them. They all are overlapping, right? They all are overlapping from each other. If you look at the data points here, they are more dense, right? Are you able to see my screen?
Yes.
Yes.
They are more dense there, right? So they are more dense here. So if you calculate the count of these data points here, the count is equal to 1. Okay, it can be any number, just it's scaled. So it means like the number of data points here is more. The number of data points in this region is this. The number of data points in this region is this. When you move further, the number of data points are getting sparse, right? Like less. So this represents the count of the data points on this axis. Okay. So that is what actually it means is. Understood? To better explain this, let me take this diagram. So I have this axis something like this. I have 10 points here. Okay, one after the other. And if I move forward, I have 5 points here. I have 2 points here. I have 1 point here. So if I draw a histogram, 10 points here, right? 5 points here, right? 2 points here, just 1 point here. So if I draw a diagram like this is what? This is how the diagram looks like. Okay. So this data points, this green color data points are these data points. This graph is derived from the histogram. Histogram is just the count of number of data points in that particular bin or in that particular region. Clear? You understood that? The graph and the data points.
Yes.
Yeah.
Okay. Now from these data points, take some samples, take some random samples and calculate the mean of that particular sample. You got the mean as this one. If you're taking 10 samples, 10 different samples from these data points, and if you calculate the mean of every sample, you got a graph something like this. And if you increased more samples, when you got more and more samples, the means of those samples will be looking like this. So the means are forming a normal distribution. So that is what central limit theorem says. Central limit theorem says it doesn't really matters what is the distribution of your population is. It can be anything. It can be any distribution. I don't care about the distribution. But if you take the mean of random samples, that particular random samples mean will form a standard normal distribution. That is what central limit theorem says. So take any kind of distribution in this entire universe. When you study any kind of data set from any kind of distribution, when you take the mean of that, it will form a normal distribution. So when you study that normal distribution, it would be something like the study would always falls down to normal distribution. In real world, most of the data sets will fall under normal distribution, and very few other distributions like random picks, like 4 or 5 normal distributions is how the data will be distributed. So if you understand how to study those distributions and different parameters that will be used to study those distributions, you will study it. The data would be very simple to understand and study or predict some information out of it. So that is what central limit theorem actually says is. Central limit theorem says irrespective of the distribution of the population, the means will form a standard normal distribution. The means will form a normal distribution. And to calculate the area under the normal distribution, the probability of a random variable taking any value between a specific range will be easily calculated by converting the normal distribution to standard normal distribution. And from standard normal distribution, you can use the Z-score table to calculate the area under the curve, which applies the same for the normal distribution as well. So you understood all the correlation between these three concepts, or from the last 3 slides that we are learning. Standard normal distribution, standardization, normal distribution, standard normal distribution, standardization using the Z-score, converting the standard normal distribution to normal distribution to standard normal distribution using Z-score, and then what the central limit theorem says. This all talks about normal distribution. Okay. And then comes, are you clear with everything till this point? Okay. And now comes the multivariant normal distribution. So till this point, we are just studying the points in 2 dimensions, right? We have not gone beyond that. Till now, you are studying only 1 dimension, basically, frankly to say. So when you look at this diagram, you might feel like it has a 2 dimensionals, right? But that's not 2 dimensional, it is 1 dimensional. The reason why it is one dimensional is, so you're drawing normal distribution something like this. Is this two dimension? This is not two dimension. This normal distribution is representing the points on one axis. So when you have more points here, you will have high length. The histogram will be, I mean, more number of students will be at average marks. Few number will be. So you are studying only one dimension. You are not studying two dimension. How does normal distribution looks like in higher dimensions is what you have to understand. Okay, which is very important to visualize the higher dimensions. As I told you, 1 and 2 dimensions is not what you study in the real world. It would be higher dimensions only. Okay, so now look at this representation. So look at this diagram. This is a normal distribution in two-dimensionality. So you have one dimension here and one dimension here. You have one dimension here, and this is how the normal distribution in two-dimensional space looks like. It is looking like a cap on the 2D space, right? Cap on the floor, right? It is forming an ellipse under the hood. If you look from the top, from a bird eye, it looks like an ellipse, something like this. From the bottom, from that it is coming like a cap, right? That is how normal distribution in a 2D space looks like. A cap on the floor, you can imagine it like that. That is how normal distribution on an, you know, 2D space looks like. If it is a 3D space, can you imagine how does it looks like in a 3D space? It is tough to imagine, right? When you go to higher dimensionalities, it is really tough to understand or visualize that. Visualization of the data points in higher dimensions would be really difficult. You can draw just up to 3 dimensions, but that's the reason why matrix came into picture. It makes the higher dimensionalities little simple. It is just like an tabular form representation of the data in higher dimensions. So we always operate on matrices, and by the from the outputs of the matrices, you can understand how the data points are distributed. But visualizing that would be really very difficult in higher dimensions. Even in 2 dimensions, look at this, it is looking very complex, right? Okay, now understand this. Multivariant normal distribution is nothing but normal distribution in higher dimensionalities. So this is how the normal distribution on 2D looks like. It looks like a cap on the floor. Try to imagine how does this normal distribution looks like in 3 dimensions. You can just take 2 minutes of time and just try to visualize how does the normal distribution looks in higher dimensions like 3D and all those things. You can just even Google that to see how the data, normal distribution data looks in higher dimensionalities. I strongly believe you will find that rarely, but okay, we covered a good amount. I just want to complete these 2 slides for today. From by tomorrow, you can see the rest of the slides. And I have the next set of slides also ready with me. But it's good to complete this part today. It doesn't take more than 15 to 20 minutes, so we should be good. All right. So now go to Google and just try to understand the diagrams or normal distributions in 3D space. If you found a good example, post that in the chat so that everyone can see. I got this diagram from the internet only, and this is how the normal distribution in 2D space looks like. Now you just try to find out how the points in how the normal distribution looks like in 3D space. Just post that in the if you find one, post that in the chat. I'll be here shortly. Just to different dimensionalities. So let's suppose understand this this way. So, you know, how does the normal distribution looks like in one dimension, right? So in one dimension, it looks something like this. Sorry. In one dimension, it actually looks like this, right? In one dimension, it actually looks like this. Now stretch this into the other dimension. So just drag this into 2-dimensional. It's really tough to draw, but if you stretch that to 2 dimensions, it looks something like this. It looks like a cap. And you have to stretch this in the other dimension continuously, something like this. You have to stretch this in the other dimension to get the 3D. So it would be something like this, and it stretches this way. Okay, so that is how you have to visualize. So stretch everything in the opposite direction to see that diagram in the 3 dimensions. So this is something like this. This is the actual diagram. You stretch that in the other dimensions and join and extend that to that particular dimension. That is how you have to visualize. But it is, as I said, it is just tough to visualize. So that's the reason we use matrix to analyze the data in higher dimensions. But understand this multivariate normal distribution is nothing but it is the distribution, normal distribution in higher dimensions. Normal distribution in d-dimensional space. Normal distribution in higher dimensional spaces like 2D, 3D, or even d-dimensional space is known as multivariate normal distribution. In d-dimensional space, instead of dealing with single numbers, we deal with vectors and matrices. So in higher dimensions, we always deal with vectors and matrices to make our job simple. You cannot visualize them. Just vectors and matrices. If you use matrix xi plus yj plus zk plus something of the sort ym, so these will be 4 dimensionals, 2 dimension, 3 dimensions, 4 dimensions, something of this sort. So vectors will make the job simple and then our analysis simple. Even matrices, 4 by 4 matrix is just like vectors in 4 dimensions. Okay. So in higher dimensions, we always deal with vectors and matrices. You will shortly see that. The normal distribution is now defined over the vectors of random variables, and the spread of the data is controlled by mean vector and covariance matrix. Okay, so from now onwards, you are getting rid of random variables. You always deal with vectors of random variables. Random variable will not be just a value from now. It will be a vector of random. It will be a vector. Okay. Till now, when you say random variable, you are talking about dice, coins, which would be a single value. From now onwards, when you deal with higher dimensions, it will always be a vector. Okay, so vector will represent 1 point. So you also have seen the dimensions on your data matrix, right? If you are studying about the different factors of your activities, like number of calories burned, number of hours you walked, number of steps you walked, all that will be one data point, which will be in vector, which is an output, which is a random variable. Okay, and the spread of the data is controlled by mean vector and the covariance matrix. Till now, what you have seen, you just have studied about covariance, right? When you in 1 dimensions or in 2 dimensions, you have in 1 dimension you have studied about variance. In 2 dimensions, you have studied about covariance and variance, and you also have studied about covariance matrix. But in higher dimensions, you always deal with covariance matrix, because covariance matrix will have all the variances between different dimensions, right? Different dimensions variances will be calculated and stored in the covariance matrix. You will use covariance matrix. Okay, so now the probability distribution function of normal distribution in higher dimensions is given by this formula. Okay, so what are replaced in 2 dimensions? Can you tell me the formula for 2 dimensions? 1 by the you remember this 1 by the root of 2 pi into sigma e to the power of x minus mu whole square by the 2 into sigma square.
Sigma to 2 pi.
So this is the formula, right? 1 by the root of 2 pi in 1 dimensions. Mean and variance are there. Now in higher dimensions, you have that sigma replaced with covariance matrix. Okay. Variance or standard deviation is replaced with covariance matrix. X minus mu whole square by 2 into sigma square. So this is replaced with covariance matrix, inverse of covariance matrix. Okay, you understood this, right? 2 into sigma square, which is the variance. This variance is coming up now, and that is becoming covariance matrix, right? So x minus mu whole square is coming down to Look at this, sigma whole to the power of 2. So variance is converting down to covariance matrix in higher dimensions. Mu value is becoming mu vector. Okay, that is the only change. So minus 1 by the 2 x minus mu whole square into by sigma square is what we got there. So x minus mu can be written as x minus mu whole transpose into x minus mu, right? In vector notations, x minus mu whole square is nothing but x minus mu whole transpose into x minus mu. It's nothing but x into x, right? And this sigma square variance is going up and becoming inverse, that is sigma to the power of minus 1. So this is converted to this in the higher dimensions. And this sigma, you have the sigma there. So sigma is nothing but root of sigma. That is sigma to the whole to the power of 1 by 2 is thought how the probability density function looks like in higher dimensions. Are you able to correlate that two-dimensional with this one? So it's just like mu is converted into mu vector, mean vector, mean is converted to mean vector, and covariance is converted to, or the covariance or variance is converted to standard deviation, is converted to covariance matrix. You also know what is covariance matrix. What are the properties of covariance matrix? What kind of matrix is covariance matrix? Is that positive semi-different matrix or negative semi-different matrix?
Positive semi-different.
A matrix is called positive semi-matrix matrix. For a matrix to satisfy the properties of to be called as positive semi-different matrix, what properties it has to satisfy?
X
Eigenvalues
transpose
should
into A
be
into
positive
X.
and true.
Yeah, that's one.
Transpose into A into X should be greater than or equal to 0.
Yeah, quadratic form should be greater than or equal to
Quadratic.
0. So we call quadratic form when we multiply that with any vector, like x transpose A into X should always be greater than or equal to 0. And what is the third one?
Symmetric.
Okay, the matrix should be symmetric, which is A transpose is equal to A. So X is a d-dimensional random vector, right? Now every point will be just not a point, it will be a vector in d dimension. Mu is the mean vector, right? Mu also will be in d dimension. Why the mu will be, let's suppose if you're taking two dimensionalities, x will look like 2 comma 3, right? Mu, for example, mu is coming as 2 comma 3. If you represent that in vector, it will be 2i plus 3j. This is the vector, right? So if it is n dimensional, it will be something like 2 into x cap plus 3 into x2 plus 4 into x3, so on x into xt, right? That is how mean vector in d dimensions looks like. Now we are expanding everything into vectors. So if it is a point in d dimensional, it would be a vector. If it is a variance in d dimensional, it would be covariance matrix. Okay, that is how you have to start analyzing in d dimensionalities. Okay, so it's just a normal distribution in higher dimensions, and you also understand how we got this formula of covariance matrix. Mean vector will become mean will become mean vector, variance will become, or covariance will become covariance matrix, variance will become covariance matrix, something like that. Okay, that is what this is. This is just a representation of 2D. So just try to imagine this. It's just like cap on the 2D floor. That's just for two dimensionalities. Okay, going back to the next thing. This is very important, and this is how you have to, this is what you have to understand, and this tells you how your understanding actually is. In two dimensionalities, the multivariate normal distribution looks like an elliptical bell curve, right? Elliptical bell curve that you have seen. So under the hood, if you look from the bird's eye, it looks something like this. So this is coming up, this is bulging up. So from the top, it looks like this, but in actual, how does it looks like? it looks like something like this. On top of this, you will just see some kind of this bulge coming on top of this. So look at this diagram, right? So below the hood, it just looks like this. On the top, it looks like cap. So we are just drawing this stuff in the next screen. Okay. In two dimensionalities, the multivariate normal distribution looks like an elliptical curve. Elliptical bell curve. The shape of the ellipse is determined by the covariance matrix. This is very, very important. The shape of the ellipse is determined by the covariance matrix. And its orientation and spread depends on the correlation between the two dimensions. Orientation and spread. Orientation and spread depends on the correlation between the two dimensions. Okay, let's understand this in a better way. If the covariance between two dimensions is 0, if the covariance is 0, what does it means? Okay. So we studied covariance, right? If covariance is positive, what does that means? If covariance is positive, what does that means?
Both are highly dependent.
Both are positive.
So if one variable increases, the other variables also increases. That is what positive covariance is. What is negative covariance? If one increases, other decreases. That is what negative covariance is, right?
Yeah.
Is that right?
Yeah.
Positive covariance and negative covariance we studied somewhere here.
Yeah.
What we studied somewhere close to here. Positive covariance means if the covariance between two variables is positive, it means that one variable increases, other tends to increase as well. Negative covariance means if the covariance is negative, it means that one variable increases, other tends to decrease. We have seen this, right? Some points like this. This is positive covariance. And if it is looking like this, it is negative covariance. If there is no relation, there it is zero covariance. We studied all this stuff, right? You remember this?
Yeah, yes.
Yeah.
Yeah. Now you are doing the same interpretation, but now with the covariance matrix. Okay. You know what is covariance matrix in two dimensions? It is sigma x square. Sorry. It is sigma x square, sigma y square, sigma xy, sigma xy. What does this say? Variance along x-axis. What does this say? Variance along y-axis. What does this say? The covariance between x and y. Right? Yes.
Yes.
Okay. So now, if this is positive, what does this say? If the values on x increases, values on y also increases. Right? Just take these examples now. Look at this diagram and just understand the interpretation of this. So here look at this 1 comma 0 0.5 0 comma 5 comma 1.5 1 0 0.5 0 0.5 1. This is the covariance matrix given to us. Now they are positively correlated or negatively correlated. The variance covariance is positive or negative. Covariance is positive or negative. This is the covariance matrix given to you. Okay, you know this is the formula of covariance matrix and these are the values given. What is the sigma x square? What is the sigma xy? What is the sigma y square? Sigma x square is nothing but the variance along x-axis, right? No? Hello.
Yes, correct. Sigma, yeah, correct.
Sigma x square is nothing but variance along x-axis. Sigma xy means covariance. When it is positive, when the value of x increases, the value of y also increases. Okay. So if you look at this diagram, as covariance is positive, when x value is increasing, y value is also increasing. Take any point. So x value is increasing, y value is increasing. When x value is decreasing, y value is also decreasing. That is what positive covariance means, right? 0.5, which is positive covariance. Look at this diagram, minus 0.8, negative covariance. That means if x value is increasing, y value is decreasing. Look at this point. Here x value is high but y value is low. When x value is decreasing, y value is increasing. They are like in different directions. That is what negative covariance means. What if one is increasing, other value tends to decrease, right? That is why the ellipse is looking like this. Can you tell me what is the mean of these two ellipses? If you by looking at the diagrams, can you tell me what is the mean of these ellipses and what is the variance of these ellipses?
Mean is 0.
Exactly, yes. What is the
And
variance
variance
along
is at
x-axis and what is the variance along y-axis?
x-axis it is 4, y-axis also 4.
No, it's not 4 just because this is the variance along x-axis, right? So that is
Okay.
1, right?
Okay, yeah, correct.
Now, look at this example. So what is the variance here? Positive, negative, 0. What is the variance? I mean, covariance.
Negative.
Covariance is negative for this diagram.
No, not for that. It is positive.
What is the value of covariance?
0.5.
What is the mean there?
Mean is 1.
So that is the reason. Look at this, mean is 1. So the ellipse centered at 1. Okay. This don't look like this circles. It is just a cap on top of the floor. You're just looking at the base of the cap. Okay. So the center of that cap is lying at 1 comma 1. And this is positive covariance means as x value increases, y also increases. Okay. And the variance along x-axis is 1, the variance along y-axis is also 1. Okay, this is something like this. That is how you have to understand these diagrams. So now look at this. What is the covariance for this? Just looking at the diagram, can you say what is the covariance for this? Is there any relation between x and y? So if x is increasing, y is increasing. So if you take this x, it has both high value of y, low value of y. If you take this example, it has high value of y, value of y. So there is no relation between x and y in this diagram. That is the reason covariance is equal to 0. So these lines, you look at these lines, it is just representation of the bulge that is coming out. So this is represented as like this here. That is how to interpret the diagrams based on the covariance matrix. now explained all that stuff. Now I'll assign this to Balli. Sai, Madhu. Is Madhu there?
No, he's not on the call.
Okay. So I want you to just re-explain me, explain me this diagram again. Clearly by looking at the values, by looking at the mean and all this stuff, why the diagram is looking like that. Someone of you can just pick your name, pick the diagram, and you can explain that. Hello? You didn't understood this? Hello?
Yeah, Mohan. So for here there is one positive and one negative, right? So there is no different. Both the pointers are completely different. So it falls under negative covariance
Why it is negative covariance?
because there is no link up between those two. Like one is in positive way, one is in negative. And
No,
mean
what
is
is the
zero, right?
covariance value? Here you are given with covariance matrix. Look at this. This is the covariance matrix given to you. Now, from the diagram, tell me what is the mean and also tell me what is the variance along x-axis, variance along
Yeah.
y-axis, and covariance.
Mean is zero.
Okay. Why mean is zero?
Uh, mm, when we are taking average, it falls under
Which average are we taking here?
uh, from the graph, we can say that mean is zero because
Yeah, from the graph, it is
center.
clearly indicated that the center of this distribution is at 0. So the
Yes.
mean is 0. Now, what is the variance along x-axis? Do you know the covariance matrix? How do we represent covariance matrix? You remember this covariance matrix, which is playing a major role there. This is the covariance matrix, right?
Yes.
So what is the saying? This saying that this is the representation of the covariance matrix. So the first says covariance of x comma 1, x comma 1, x1 comma x1. That is nothing but the variance along the x1 axis. Covariance of x comma x2 is nothing but the covariance of x1 comma x2. It says like how does the values on x1 is impacting the values along x2. That is covariance matrix says, right?
Yeah.
And similarly, covariance x2 comma x2 means how does this is nothing but a variance along x2. because x2 minus mu whole square, x2 minus mu whole square will become x2 minus mu. I mean, x2 minus mu into x2 minus mu will become x2 minus mu whole square. And again, that is converting back to variance along x2. And covariance x2 comma x1 is nothing but the covariance of x1 comma x2. These two will be the same. Now, you are given this covariance matrix. The covariance matrix is given as 1 comma 0.8, 0.8 comma 1. Right? This is what it is given to you. 1 minus 1, 0.8 minus 0.8, 1. So what is this minus 0.5 says? Is this covariance or variance?
Covariance.
That is covariance, right? So the negative covariance means how does the values on x impact y? Okay, I think most of the stuff is not clear to you, clear to most of us. So just raise your hands who got this concept cleared, like who has clear understanding of what we are talking here. Because this is accumulation of so many stuffs, variance, covariance matrix, mean vector, and all these things. So did anyone completely understood this? Now coming back here, in 2D, the probability density function of a multivariate normal distribution form concentric ellipse around the mean. That is what you have seen. This is what you have seen, concentric ellipse around the mean. Each ellipse represents a level of probability density like a contour map. These are all the contour maps. These are called as contour maps. Contour maps is just like probability, I mean, on a single dimension, I could say. The axes of the ellipse are determined by the eigenvectors of the covariance matrix. The axes of the ellipses are determined by the eigenvectors of the covariance matrix. The length of the axis is determined by the eigenvalues, which tells you how spread out the data is in those directions. Okay. What you have understood from this is you already know eigenvalues determines the spread, right? Whether it is positive or negative. Eigenvectors represents the axes. Okay. So now if you take the covariance, what this slide is saying is, this is also very important. What this says is, if you calculate the eigenvectors of the covariance matrix, if you calculate the eigenvectors of the covariance matrix, they represents the axes of the ellipse. What are the axes of the ellipse? These are the axes of the ellipse. So this is one of the axes of the ellipse. This is one of the axes of the ellipse. This is called major axis and this is called as minor axis. Okay. So these axes are represented by the eigenvectors of the covariance matrix. And the stretch of this ellipse will be decided by the eigenvalues. So you might have calculated this vector with an eigenvalue, right? You might have calculated this vector with eigenvalue, because without eigenvalue, you cannot get the eigenvector. So the eigenvalue associated with eigenvector will determines the stretch of this matrix. Understood? And the eigenvalue used to calculate this vector, this eigenvector, is the stretch of this ellipse in that particular direction. So eigenvalues gives the stretch, eigenvectors represents the axes of the ellipse. Okay, so this is the axis, this is the axis. The lambda used to calculate this will be represented, will give the length of this ellipse. The eigenvalue used to get this vector will give the eigenvalue, I mean, the stretch of this ellipse in that direction. Is that clear? Understood. Eigenvectors are the principal axes of the ellipse or the contour. Eigenvalues represents the stretch of the ellipse. The length of the axis is determined by the eigenvalues, which tells you how spread out the data in these directions. So eigenvalues represents the spread. These are all the data points, right? This spread is given by the eigenvalue, and the direction will be given by the eigenvector. Similarly, eigenvalue will give the spread of the data in this direction. So spread means this is spread, this is spread, this is spread in this direction, and this is spread in this direction. Those will be given by the eigenvalues. So by tomorrow, I just want to make sure you are all clear with these concepts. And then we can start from Mahabolinis distance from tomorrow. These are all very sample things. I just have to add chi-square test. With that, we are done with all the basics. And then we will start working on analyzing the data in higher dimensions. We do dimensionality reduction as the next thing. What dimensionality reduction is basically means, you just have to understand what is dimensionality reduction. So now we know what is covariance, what is correlation, and what is variance and all the stuff, right? Let's take an example of the movie. Okay. When you say movie, it has different parameters like actors are there, genre is there, and it can be budget will be there, and also what director will be there, hero will be there. So these are all attributes of the movie, right? Hero, actors, genre, budget, and all. So out of these parameters, these are all different dimensions. So how many dimensions are there now? We have 5 dimensions are there. So dimensionality reduction means the word itself says you're reducing the dimensions to better understand any new movie. Okay, to better understand any new movie, or to understand the existing data so that you can make the budgets accordingly. So when you want to produce a new movie, you want to study this data and then do the next movie with that set of, you can produce the movie so that it will be a bigger hit. So you have to study the existing data. Now, do you have to consider all these parameters? All these parameters have equal importance. So all these have same weightage, or do you think they have different weightages? Do you think anything has nothing to do with the movie hit or not? Do you have budget as a parameter to make sure a movie is hit or not? It might have a value, but even if you ignore that, I mean, that is not a big deal. Budget, even a low budget can collect a high revenue. Even high budget movies can fail, right? Budget is not a parameter to study. What you have to study? You have to study genre. Out of all these things, what is more important is the story of the movie. It has a very high weightage, right? And the director's crew will have some weightage. So this dimensionality reduction is basically what it will do is it finds out what attributes are more important and what attributes are less important. If an attribute is not important, just ignore that attribute. So you no more consider that attribute. Okay. So if budget is not important, ignore this, remove this complete column or complete dimension from our analysis. So that part of study is called as dimensionality reduction. Okay. Choose some dimensions in your data, choose only few dimensions in your data, or consider every dimension, but change that to fewer dimensions. So this is 5 dimensions, 5 dimensionality. Now what I'll do is reduce the dimensionality. I will plot all this data into 3 dimensions by just merging few dimensions. Let's suppose I come up by, I'll just add all these 3 dimensions like hero, actors, and directors. All this comes under crew. Now what I'll do, I'll merge these 3 dimensions and mark them as crew. I'll make it as single dimension. So that is one kind of dimensionality reduction. Combining multiple dimensions and making it as one dimension is one part of it. And the other part is just ignore some dimensions completely from the data and just do the analysis with the existing data. That is one part of another part of dimensionality reduction. So we call them as future selection and future scaling. Those are two different steps of dimensionality reduction: future selection and future construction. Future construction, what I have said, you will construct the futures. You will construct the dimension based on different dimensions. That is called as future construction. Future selection means you will select out of 5, you just select randomly 3 different dimensions. So how to do that and what is the best way of do that to analyze the data better is what you are going to study. That actually relates to, most of that is related to pre-processing stuff. As I told you, pre-processing, model construction and model testing. So we will start with pre-processing phase. In pre-processing we do all this stuff, dimensionality reductions and all that stuff. We will start with dimensionality reductions starting from tomorrow. So by then what I want to make sure is you're clear with all the basic concepts. So we almost done up to this slide, right? We are very much close to completing the basics, but where are we now? We are at 37 slide. I just have 10 more slides to complete all the basics. So you should be familiar with everything that we have discussed so far, so that you will be the rest of the part would be little easier if you understand all this stuff. So I just request you